Hello there and welcome to Science for Sleep, where we let curiosity settle in beside us and science takes its time. Tonight we are beginning a journey that looks not just outward from our home among the planets, but also upward and downward, if such directions even make sense in the quiet of space. We're going to ask, very simply, what is above our solar system and what is below it? It sounds like a straightforward question, the kind of thing that might have a simple answer, like pointing toward the ceiling or toward the floor. But in the vastness of the cosmos, where there is no true ceiling and no true floor, the answer becomes layered, surprising, and worth exploring at a slow and steady pace. Before we begin unfolding what lies beyond the reaches of our familiar solar neighbourhood, I'd like to pause with you for a moment and ask something simple. Where are you listening from tonight? Are you tucked in bed, eyes heavy after a long day? Are you on a couch with a cup of tea nearby? Or maybe it's morning for you, and you found this corner of quiet curiosity while the rest of the world is just waking up. In your own little place on Earth, under your own patch of sky. You're sitting inside a solar system that itself sits inside a galaxy, which itself sits inside something even larger. The direction above you and the direction below you stretch out into distances so immense that they almost become difficult to picture, and yet here you are, a part of it all. If you find that this way of learning slowly and gently helps you to rest, to wonder, or simply to let the day slide away a little easier, it would mean a great deal if you supported this channel by liking this video or subscribing. It helps this small space of calm reach others who might also need a pocket of peace among the noise of daily life. And with that, let's make ourselves comfortable, take a deep breath, and begin to wander into the question of what lies above and below the solar system. The first thing to notice is that above and below are words we normally use on Earth. Words tied to gravity, to floors, to ceilings, to the sense of orientation that our bodies naturally expect. In space, though, things are more flexible. There is no single up and no single down. Instead, astronomers create a kind of agreed-upon map. They take the plane of the solar system, the flat sheet traced out by the orbits of the planets, and call that the reference. From that plane, there is a direction pointing one way, which they call north, and another direction pointing the opposite way, which they call south. Above, then, becomes north of this plane, and below becomes south of it. Already we can see how human definitions shape our view. When we talk about above, we mean the direction that follows the north pole of Earth's spin, extended outward into the galaxy. When we talk about below, we mean the opposite. It may feel strange to think that these words we use so casually on Earth, words that help us climb stairs or look for a ceiling light, are stretched all the way into space, where they keep their usefulness even without walls or floors. But they matter because they give us orientation. They let us say with some confidence what lies in one direction and what lies in the other. And with orientation we can begin exploring. As soon as we start asking what lies above, we run into something important. Our solar system isn't just floating naked in space. It is wrapped in a bubble, an invisible one, made by the very breath of our star. The sun is constantly releasing a stream of charged particles known as the solar wind. This wind rushes outward in all directions, filling a vast region of space around us. Where that wind still pushes outward strongly, we are within the solar system's protective bubble. Where the push of the solar wind finally balances against the push of the thin interstellar gas outside, there lies the boundary. A shifting frontier known as the heliopause. Above us, beyond the orbits of the planets, beyond even the icy realms where comets sleep, this bubble stretches for billions of kilometres. It shields us from a large portion of the high-energy particles that zip through our galaxy. Astronomers often describe it as if our sun were a boat cutting through a sea of thin cosmic matter, with the heliosphere acting like the bow wave. Above the plane of the solar system, as much as below it, this bubble extends. It is the first answer to the question of what surrounds us, the invisible skin of the sun's influence. If we look farther still, we begin to leave the reach of the solar wind. There the space between stars becomes the setting. It may sound like emptiness, but in reality it is filled with wisps of gas, dust and radiation. It is called the interstellar medium. Above the solar system lies part of this medium, a particular pocket of it that astronomers call the local interstellar cloud. This cloud is not dense by earthly standards. A single cubic centimetre might contain just a few atoms, where the air you breathe contains billions of billions. But on the scale of space, that is enough to matter. It shapes how the heliosphere is squeezed. It contributes to the balance of pressures around us. And it means that above us is not empty nothingness, but rather the thin breath of the galaxy itself. When astronomers map these regions, they often talk about looking toward the North Galactic Pole. This is the direction that is above not just the plane of our solar system, but above the plane of our galaxy as well. Imagine our galaxy as a giant disk, flat and wide, with spiral arms curling outward. From our location within one of those arms, above means looking up out of that disk toward the galactic north. That direction takes us out of the crowded band of stars that we see as the Milky Way in the night sky, and into a sparser background filled with distant galaxies. Below means the opposite, looking toward the galactic south. Both directions are fascinating because they take us out of the thick fog of our own galaxy's stars and into clearer windows through which we can see the universe beyond. As you picture this, you might start to feel small, almost like a passenger on a ship with no end in sight. But there is comfort in knowing that these orientations help us make sense of it all. We can say that above the solar system lies the heliosphere's outer edge, the interstellar medium, and beyond that the galactic halo, an extended region filled with dark matter, ancient stars and globular clusters. Below us the same structures mirror back, reminding us that the universe is not a tower with a roof and a cellar, but a wide open expanse where directions are relative. Thinking about these things as you settle into your evening is not meant to unsettle you. Quite the opposite. The more we recognise that we are surrounded by these vast layers, the more grounded we can feel on our small blue planet. Every star overhead, every soft patch of night sky, every moment of quiet is a reminder that we're at home in something enormous, but also something that can be understood step by step. And so we begin here, asking gently what is above, what is below, and realising that even this simple question can take us far beyond where we thought we would go. When we try to set the stage for a journey through what lies above and what lies below our solar system, the first thing we need is perspective. The solar system itself is not floating in isolation. It is moving, shaped, and guided by larger patterns. To understand what lies above and beneath, we have to picture how the whole structure is arranged, like preparing a map before taking a walk. Even though space does not give us the clear up and down that we know on Earth, scientists and explorers of the cosmos have built a framework that lets us talk about direction, orientation, and position with confidence. This framework is what allows us to say, with some clarity, what exists above us and what lies beneath. The foundation of this framework begins with the plane of the solar system. If you imagine all of the planets orbiting around the Sun, you can picture how they mostly share the same flat sheet of space. The orbits are tilted slightly, some a little more, some a little less, but overall they form a disc-like structure. That plane, defined most precisely by the orbit of Earth, is called the ecliptic. It is our cosmic baseline, the reference surface we use when talking about above and below. From that baseline, astronomers extend lines outward. The north direction is aligned with the spin of Earth, continuing outward through the solar system, and the south direction is the opposite. With those two directions established, we now have something resembling the concept of up and down. But instead of pointing to a ceiling or a floor, these directions point towards different regions of our galaxy. It may sound arbitrary, but this choice gives us the ability to organise our thinking. When we speak of above, we mean toward the North Galactic Pole. When we speak of below, we mean toward the South Galactic Pole. This orientation is not just a trick of naming. It matters because the Milky Way itself is shaped like a flat disk. Most of its stars, gas and dust are concentrated in that thin plane. Above and below take us out of the disk, away from the crowded plane of stars and into clearer regions that stretch toward the galactic halo. In other words, once we set the stage this way, above and below become directions that let us step outside the main crowd of the galaxy and peer into what surrounds it. The solar system, then, can be pictured like a bead lying in the middle of a great spinning disk of stars. Around us, the local neighbourhood of stars forms the spiral arm we live in, the Orion arm, a small branch of the Milky Way. Above the solar system lies the emptying sky of the galactic north. Below lies the matching emptiness of the galactic south. Both regions are less crowded with stars than the bright band of the Milky Way itself. When you step outside on a clear night and see the Milky Way stretching across the sky like a faint river of light, you're looking along the disk. But if you lift your eyes away from that band and gaze into the darker patches, you're looking in the direction of above or below. The stage also requires us to consider scale. On the small end, we have the solar system itself, extending far beyond the familiar planets. The orbit of Neptune, the outermost major planet, is only the beginning. Beyond that lies the Kuiper belt, filled with icy objects, dwarf planets and comets. Even farther in theory lies the Oort cloud, a vast spherical shell of icy bodies surrounding the solar system at a distance so great that it may stretch nearly halfway to the next star. That cloud marks the edge of the sun's gravitational influence. If we think about above and below on that scale, we are talking about regions where comets rest quietly until something disturbs them. On the larger end of the scale, above and below reach into the galactic halo. This halo is a faint extended region surrounding the flat disk of the Milky Way. It contains ancient stars, remnants of smaller galaxies consumed by our own, and a great deal of invisible dark matter that holds the galaxy together with its gravity. Above us lies the northern part of that halo. Below us lies the southern. Both are equally strange, equally filled with objects that tell stories about the earliest times in the galaxy's history. When we set the stage in this way, we start to see how above and below are not just casual directions, they are routes to discovery. Looking above, we see less interference from the gas and dust of the galactic plane, giving astronomers clearer windows to observe distant galaxies and the cosmic background radiation. Looking below, we see a similar window in the opposite direction. Both are vantage points for understanding not just our solar system, not just our galaxy, but the universe as a whole. It is worth remembering, too, that the solar system itself is not sitting still. As part of the Milky Way, it is orbiting around the galactic centre at an impressive speed, roughly 828,000 kilometres per hour. That orbit takes about 225 million years to complete. As the solar system moves along this immense path, it also bobs slightly above and below the galactic plane, like a bead on a string that wobbles as it circles. Over tens of millions of years we drift upward, then downward, then back again. This oscillation shapes how we encounter different regions of interstellar space, how cosmic rays reach us, and perhaps even how Earth's history has unfolded. By setting the stage in this way, we begin to see how above and below are not static at all. They are directions through which we are constantly moving. This stage is also filled with unseen players. One of them is dark matter, a mysterious form of matter that does not emit light yet exerts gravitational pull. Astronomers believe that the halo surrounding the Milky Way is rich in dark matter. Above and below, then, are not empty expanses. They are regions where this invisible material shapes the motions of stars and galaxies. Though we cannot see it directly, its presence is inferred from the way galaxies rotate and the way light bends as it passes through space. It is a reminder that much of what lies above and below is still hidden from us, waiting for clearer instruments and deeper understanding. As you picture this stage, it helps to remember that scale can change our perception. Above and below might mean the space just beyond Pluto, where icy fragments drift in silence. or it might mean the immense distances beyond the galactic disk where faint globular clusters orbit in the halo. The words are the same, but the distances involved can be trillions of times greater. This layering of scales is what makes the question both simple and profound. By setting the stage carefully, we leave room for all of these meanings. When we imagine our place in the galaxy, it is tempting to feel dwarfed by the immensity of it. But the very act of mapping above and below, of giving ourselves a framework to talk about these directions, shows the power of human thought. We have taken concepts that make sense in a room or on a planet and stretched them to fit the galaxy itself. In doing so, we've created a way to explore. Without that framework, the cosmos might feel too disorganized to discuss. With it, we can talk calmly about what lies above, what lies below, and how they connect. The stage is also marked by light. Above the solar system, when astronomers lift their telescopes, they find the faint glow of background radiation left over from the Big Bang. Below the solar system, they find the same. This radiation is evenly spread across the universe, yet the paths we take to see it are shaped by what lies in our line of sight. The galactic disk, thick with stars and gas, can obscure it, but above and below the view clears, and the radiation shines through more cleanly. This gives astronomers one of the best tools they have to study the early universe. The stage we're setting, then, is not just about our local neighbourhood, but about the deepest history of everything. There is also movement in this stage. Cosmic rays, high-energy particles born in distant explosions, stream toward us from all directions. The heliosphere deflects some of them, but not all. Above and below, these rays pour in, carrying with them information about the violent events that shape the galaxy. By studying their arrival, scientists can trace where they came from, how they travelled, and what they tell us about the structure of space. The directions above and below are part of that study. If all of this sounds like a lot to hold in mind at once, it is, but it is also what makes the stage worth setting. The solar system is not a simple bubble floating in nothing. It is part of a complex environment, with layers, boundaries, movements, and histories. Above us lies one path through those layers. Below us lies another. Together they form the stage on which we now begin to look more closely. The idea of above and below will guide us as we move forward. Every structure we describe, every region we visit will be understood through this orientation. And slowly, gently, we will build a picture of where we sit in the grand arrangement of the cosmos. The idea of the solar system floating inside a bubble may sound like imagination, but it is one of the most real and most important structures surrounding us. The sun is not a quiet ball of light simply shining in space. It is a star in constant motion, throwing out streams of charged particles every second of its life. This stream, known as the solar wind, travels in all directions at hundreds of kilometers per second. As it flows outward, it carves a bubble around the solar system. That bubble is called the heliosphere, and it is the reason we live inside a sheltered region, rather than directly in the raw environment of interstellar space. To understand the solar bubble, we need to picture what the solar wind actually is. At its heart it is plasma, a mixture of protons and electrons set free from the outer layers of the sun. The sun's atmosphere, called the corona, is so hot that particles there have enough energy to escape the sun's gravity. Once they escape, they are swept outward by the sun's magnetic field, carried into the far reaches of space. These particles don't stop. They keep going until they run into something strong enough to push back. For billions of kilometers, there is almost nothing to stop them. This is why the heliosphere grows so large. The heliosphere has several layers, though they are not like walls you could touch. They are more like gradual transitions in a flow of wind. Closest to us, the solar wind streams freely. Farther out, it begins to slow as it meets the thin gas of interstellar space. That slowing creates a boundary called the termination shock. Beyond it, the solar wind becomes turbulent, compressed, and heated. Even farther still lies the heliopause, the outer boundary where the pressure of the solar wind and the pressure of the interstellar medium balance each other. This is the true edge of the solar bubble, the place where the influence of our star gives way to the influence of the galaxy. Above the solar system, below it, to every side, the heliosphere extends. It is not perfectly round. Because the solar system moves through the galaxy, the bubble is thought to be shaped more like a comet, with a rounded front facing the direction of motion and a long tail trailing behind. In that front region, the solar wind is compressed, pushing hardest against the oncoming flow of interstellar particles. Behind us, the bubble stretches farther, thinned out by the relative ease of the solar wind expanding into space. This asymmetry is important because it shapes how cosmic rays and other particles enter our neighbourhood. Depending on whether they come from above, below, or the sides, their paths may be blocked or redirected differently. The size of the heliosphere is staggering. From the Sun to Earth is about 150 million kilometres. From the Sun to the termination shock is more than 14 billion kilometres. From the Sun to the heliopause is around 18 billion kilometres, though the distance changes depending on solar activity and direction. To put that into perspective, it takes light about 8 minutes to travel from the Sun to Earth. It takes light over 16 hours to cross from the Sun to the edge of the heliopause. This immense bubble defines the region we call the solar system in a very real way, not by orbits of planets, but by the reach of the Sun's breath. We know what we do about this boundary thanks to a handful of spacecraft that have travelled farther than any others. The two Voyager probes, launched in 1977, have spent decades moving outward. Voyager 1 crossed the heliopause in 2012. Voyager 2 crossed in 2018. The instruments recorded the change as the solar wind faded and the influence of the interstellar medium increased. It was a slow transition, but a clear one. They confirmed that the bubble exists, that it has a boundary, and that beyond it lies the true environment between the stars. These spacecraft are still sending signals back, faint whispers travelling across unimaginable distances, giving us the first direct samples of what lies beyond the solar bubble. Why does this bubble matter so much? One reason is radiation. The galaxy is filled with high-energy particles, cosmic rays born from supernovae and other violent events. These particles are dangerous. They can damage DNA, disrupt electronics, and strip away atmospheres. The heliosphere acts as a shield, blocking many of them from reaching the inner solar system. Without it, Earth would be bombarded with far more radiation than it is. The magnetic field of Earth provides a second layer of defence, but the heliosphere is the first line. It is not perfect, but it is vital. The bubble also matters for how we think about boundaries. When we talk about the solar system, we often think about planets and dwarf planets, about the Kuiper belt and the Oort cloud. But in a different sense, the solar system is defined by this bubble. As long as the sun's wind has influence, we are inside its domain. Beyond that, we are in the galaxy proper. This is why the Voyagers crossing the heliopause was such a historic event. They became the first human-made objects to truly leave the sun's protective reach. Above the solar system, the bubble stretches into regions that astronomers map carefully. They compare the density of interstellar gas in different directions. They measure how the solar wind slows and bends. They study how cosmic rays leak in through certain areas more than others. These details help them understand the shape of the heliosphere, which is still not fully known. For decades it was thought to have a long tail like a comet. More recently, some evidence suggests it may be shorter and more rounded, shaped by complex magnetic fields. Whatever the exact form, above and below are part of its structure, they are not empty. They are filled with the turbulent edge of the sun's influence. This solar bubble also changes over time. The sun's activity rises and falls in cycles of about 11 years. During the active part of the cycle, the solar wind grows stronger, pushing the boundaries of the heliosphere outward. During the quieter part of the cycle, the wind weakens, and the boundaries shrink inward. This breathing in and out means that the edge of the solar system is not fixed. It moves, sometimes by billions of kilometres, Above us, below us, these boundaries are always shifting, expanding, contracting, responding to the rhythm of the sun. The idea of a bubble also reminds us that we are not the only ones with such protection. Other stars with winds also carve bubbles in space. These bubbles can press against one another, overlap, or leave gaps between them. Our heliosphere is one of countless such structures scattered throughout the galaxy. Above us and below us, beyond the heliopause, lies the larger environment of overlapping bubbles, cavities and clouds, a patchwork of stellar influence. By studying our own bubble closely, we learn how stars shape their surroundings everywhere. Another reason the bubble matters is exploration. Any spacecraft heading out of the solar system must eventually cross it. The environment inside the heliosphere is one thing. The environment outside is another. Engineers and scientists preparing for interstellar probes need to understand what lies ahead, how particles and magnetic fields behave, what kind of radiation levels will be encountered. The Voyager data is a beginning, but it is only 2 points in 2 directions. To truly know what is above and below, more missions will be needed. The solar bubble also connects us back to Earth in an indirect way. When solar storms erupt, sending bursts of energetic particles, they travel outward on the solar wind. Some of them reach Earth, disturbing our magnetic field and creating auroras. Others continue outward, shaping the structure of the heliosphere itself. Above and below the solar system, far from Earth, those disturbances ripple through space. They remind us that even at the edge of the bubble, what happens on the sun can still be felt. Thinking about the solar bubble as the edge of our sun's breath makes it easier to picture. Every moment the sun is exhaling, that breath stretches out, filling a vast sphere, pressing against the thin gas between the stars. Where the breath ends, where it meets resistance, the bubble closes. Inside, we live under the influence of one star. Outside, the galaxy takes over. Above us and below us, that transition is real, sharp, and yet invisible to our eyes. When you look at the night sky, it may not feel like such a bubble is there. The stars look close, the space between them looks open. But all the while, we're inside this shield, protected by the constant flow of particles from the sun. Setting the stage in this way, and then realizing the bubble we live in, brings a new kind of perspective. Above us and below us is not only the galaxy, it is also this immense, ever-changing shield, wrapping us in the breath of the star that gave us life. The bubble we described as the reach of the sun's breath has another name that is used more often in scientific discussions. It is called the heliosphere. The word comes from helios, meaning the sun, and sphere, meaning the region it fills. It is more than just a description of the solar wind flowing outward. It is an entire system of structures, layers, and boundaries that together create a cocoon around our solar system. When we talk about being sheltered from the larger galaxy, this cocoon is what we mean. It is not visible to the eye, yet it is one of the most important shields we live within. The heliosphere stretches far beyond the outermost planets. If you think of Neptune, the farthest major planet, orbiting at around 4.5 billion kilometers from the Sun, you can then compare that to the heliopause, which can be more than 18 billion kilometers away. This means the heliosphere extends several times farther than the most distant planet. In fact, it is so large that most of the solar system, as we imagine it with planets and asteroids, fits comfortably inside with room to spare. It is not a thin bubble, but a thick, expansive one. Inside this cocoon, the solar wind flows outward at high speed. It carries with it the magnetic field of the sun, stretched out and twisted by the rotation of the star. This extended magnetic field is known as the heliospheric magnetic field, and it forms a spiral pattern because the sun spins as it blows out the wind. Imagine a lawn sprinkler sending out streams of water while turning. The streams curve as they move away. In much the same way, the sun's magnetic field spirals through space, filling the heliosphere. Above us, below us, and all around us, this spiral structure shapes how charged particles move. how cosmic rays are deflected, and how energy flows in our neighbourhood of space. One of the key roles of this cocoon is to act as a barrier against galactic cosmic rays. These particles, accelerated to near the speed of light by distant supernovae and other energetic events, would bombard our solar system directly if not for the heliosphere. Instead, many of them are deflected, slowed, or scattered at the boundary. The heliosphere does not block them completely, but it reduces their intensity. Without this protective cocoon, Earth and the other planets would be exposed to far higher levels of radiation. For life on Earth, and for the technology we depend on, this shielding is essential. The shape of the heliosphere has been debated for many years. For a long time, scientists believed it resembled a comet, with a rounded nose facing the direction of the solar system's movement through the galaxy, and a long trailing tail stretching behind. More recently, data from spacecraft and simulations have suggested it may instead be more like a rounded bubble, with no long tail shaped by complex magnetic interactions. Whichever exact shape turns out to be correct, what matters is that it is not uniform. The heliosphere is squeezed in some directions, stretched in others, constantly reshaped by the push and pull of interstellar matter outside and the rhythm of the solar wind inside. Above and below the solar system, the heliosphere may extend differently depending on how the pressures balance. It is a living boundary, not a fixed wall. The Voyager spacecraft gave us our first direct evidence of this cocoon. As they travelled outward, they passed through the termination shock where the solar wind slows down abruptly. They moved into the heliosheath, the turbulent region just inside the heliopause, and eventually crossed into interstellar space. The data they sent back showed the drop in solar particles and the rise in interstellar particles. They confirmed that the cocoon exists, that it has structure, and that crossing it is a measurable event. These discoveries were not just technical milestones, they were the first time humanity touched the boundary between our star's domain and the galaxy beyond. The heliosphere also connects to Earth in ways we feel more directly. When solar activity is strong, the heliosphere grows more inflated, pushing its boundary farther outward. During quiet times, it contracts. This breathing in and out influences how many cosmic rays reach Earth. For example, during periods of strong solar activity, when the heliosphere is larger, fewer cosmic rays penetrate to the inner solar system. During quiet periods, more do. This variation has been linked to changes in climate and weather patterns on Earth over long timescales. It is a reminder that our planet is not only affected by local conditions, but by the rhythm of the cocoon we live inside. Understanding the heliosphere is also crucial for human exploration. If humans are to travel beyond Earth, beyond the protective magnetic field of our planet, and into deep space, they will need to contend with the radiation environment shaped by the heliosphere. Spacecraft electronics already face this challenge, but for human health, the stakes are higher. Knowing how the cocoon works, how it shields, and where its weaknesses lie, is part of preparing for journeys farther than the Moon or Mars. Above us and below us, beyond the safe haven of Earth's magnetosphere, the heliosphere is our broader shield. The cocoon is not just passive, it interacts with the interstellar medium outside. Where the two meet, turbulence forms, magnetic fields twist and reconnect. Particles are accelerated. This boundary region is not calm. It is active, changing, and filled with processes we are still learning to understand. Studying these processes tells us not only about our own cocoon, but also about the environments around other stars. Each star has its own version of a heliosphere, often called an astrosphere. By comparing them, we can learn how stars shape habitability, how they shield planets, and how they interact with the galaxy. Our heliosphere is just one example in a cosmic population of protective cocoons. The size and influence of the heliosphere are also connected to the age and activity of the Sun. Young stars tend to have stronger winds, creating larger and more forceful astrospheres. Older stars may have weaker winds, shrinking their cocoons. Our Sun, at about 4.6 billion years old, is in middle age, and its heliosphere reflects that. Above and below, in every direction, the cocoon is balanced between the strength of the solar wind and the resistance of the interstellar medium. Over time, as the sun ages and its activity changes, the cocoon will change too. Billions of years from now, when the sun evolves into a red giant, the heliosphere will expand differently, eventually fading as the star loses much of its mass. The cocoon we live in is not permanent. It is tied to the life of the star itself. Scientists study the heliosphere not only with spacecraft, but also with observations of distant stars. When starlight passes through the boundary of another star's astrosphere, it leaves signatures in the light spectrum. By studying these signatures, astronomers can infer the properties of those cocoons and compare them with our own. In this way, the heliosphere becomes a model, a local example of a universal phenomenon. Above and below us throughout the galaxy, billions of such cocoons exist, each one sheltering its own planetary system. The heliosphere can also be thought of as part of a larger chain of shields. At the smallest scale, Earth has its own magnetic field, which deflects solar particles and cosmic rays. Around that, the heliosphere provides another layer of protection. Around that still, the galaxy itself has magnetic fields that influence how particles move. At each scale, there is a cocoon, a shield, a structure that shapes the environment within. The heliosphere is our middle shield, between the local defence of Earth and the larger environment of the Milky Way. For all its importance, the heliosphere is still mostly invisible. We cannot step outside and see its outline. We know it only through measurements, through the way particles behave, through the faint signals carried back by distant spacecraft. And yet, though unseen, it is always there. It is the reason cosmic rays are not as deadly as they could be. It is the reason Earth's environment has been stable enough for life to evolve. It is the quiet cocoon around everything we know. Thinking about this cocoon as you drift into rest can bring a strange kind of comfort. It reminds you that even in the openness of space, there are layers of protection. Our star, in addition to giving us light and warmth, also gives us shelter. Its constant outflow forms a vast shield, extending far beyond anything we normally picture when we say solar system. Above and below, it wraps around us, not like a solid wall, but like a great invisible breath, a cocoon in which we all live. When we step past the edge of the heliosphere, we find ourselves in a new kind of environment. It is no longer the familiar domain of the sun's influence, no longer the solar wind streaming freely, no longer the protective cocoon that defines our immediate home. Instead, we arrive in what astronomers call the interstellar medium, the space between stars. At first thought, it might sound like emptiness. After all, the distance from one star to another is measured in light years, and even light travelling at nearly 300,000 kilometres per second takes years to cross it. Surely such a space must be empty. And yet, it is not. It is filled with thin gas, dust and fields that weave together to create a quiet but complex environment. The interstellar medium is not uniform. It has structure, texture and variation. Much of it is extremely diffuse, with just a few atoms per cubic centimetre. Compared to the air around you, which contains roughly 10 billion molecules in the same volume, this is nearly nothing. But across cosmic distances, even a few atoms matter. Over light years, those atoms accumulate, shaping the movement of stars, guiding the formation of new ones, and absorbing and scattering light. The interstellar medium, sparse as it seems, is the raw material from which stars are born and into which they return their matter when they die. Within this medium, there are denser regions that astronomers call interstellar clouds. These clouds are concentrations of gas and dust, sometimes only slightly denser than their surroundings, sometimes thousands of times more so. They vary in size from small wisps to enormous complexes stretching for hundreds of light years. They are the features that give the interstellar medium its character, its structure, and its role in galactic life. Above the solar system, below it, to every side, such clouds surround us. The solar system happens to be passing through one right now, known as the local interstellar cloud. It is a relatively warm and diffuse cloud, about 30 light-years across, made mostly of hydrogen and helium atoms. The Sun entered this cloud within the last few tens of thousands of years and will leave it again in tens of thousands more. In cosmic terms, this is a brief visit, but for us it defines our current environment. The boundaries of this cloud influence the shape of the heliosphere, squeezing it or allowing it to expand depending on the density and pressure of the gas outside. Above us and below us, the local interstellar cloud stretches, shaping the way our solar bubble interacts with the larger galaxy. Interstellar clouds come in many forms. Some are warm, like the one we're in now with temperatures of several thousand degrees. Others are cold, just a few dozen degrees above absolute zero. In those cold clouds, molecules can form, and in the densest regions, gravity can gather matter into knots that eventually collapse into new stars. These dense molecular clouds are often called stellar nurseries because they are the birthplaces of stars and planets. Seen from Earth, they appear as dark patches in the Milky Way, where the dust is so thick that it blocks the light of background stars. In other places they glow faintly, lit up by nearby starlight. Above the plane of the solar system and below it, such clouds drift, waiting for the right conditions to spark the birth of new suns. Dust is another part of these clouds. Tiny grains, often smaller than a micron, made of silicates, carbon compounds and ices, float through the interstellar medium. They are sparse but not negligible. When light from distant stars passes through regions rich in dust, it is dimmed and reddened, a process known as interstellar extinction. This effect is why some parts of the night sky look darker than others, why the Milky Way has lanes of shadow cutting through it. Dust is not just an obstacle, though. It is also a building block. Those grains are the seeds around which molecules gather, the ingredients that eventually form planets, moons, and everything solid. The dust above us and below us is, in a very literal sense, the material from which new worlds will one day be made. Magnetic fields also thread through the interstellar medium. They are weak compared to the fields we know on Earth, but across vast distances they guide the motion of charged particles, shape the structure of clouds, and influence the birth of stars. They give the interstellar medium an unseen skeleton, lines of force that bend and twist the gas. When astronomers observe the polarized light of distant stars, they can trace these magnetic fields, mapping how they run above and below the solar system, how they wrap around clouds, and how they shape the space between. The interstellar medium is also where shock waves from supernova travel. When a massive star explodes, it sends out a blast wave that plows through the surrounding gas, compressing it, heating it, and stirring it into motion. These shock waves can trigger the collapse of nearby clouds, sparking new star formation. They also enrich the medium with heavy elements, the products of nuclear fusion inside the star. Without this recycling, the galaxy would not have the carbon, oxygen and iron that make up planets and life. Above and below the solar system, shockwaves from ancient supernovae have passed countless times, shaping the clouds we now drift among. It is interesting to consider that the local interstellar cloud itself may be the result of past supernova explosions. Astronomers believe our solar system resides in a larger cavity called the local bubble, a region of low-density gas carved out by multiple supernovae over the past 10 to 20 million years. The local cloud is a denser region within this bubble. If that history is correct, then the very space around us is a product of stellar death and rebirth. Above us and below us, the traces of those explosions remain, faint echoes in the structure of the medium. The interstellar medium also plays a role in how we see the universe. Radio waves, X-rays, ultraviolet light, all are absorbed or scattered to varying degrees by the gas and dust. To study distant galaxies or the cosmic background radiation, astronomers must account for this interference. Above the solar system, in directions where the interstellar medium is thinner, clearer views are possible. Below the solar system, similar windows exist. These transparent paths are like keyholes through which we can peer deeper into the cosmos. For spacecraft travelling beyond the heliosphere, the interstellar medium is the environment they must navigate. It is not empty, but filled with a constant drizzle of atoms, dust grains and radiation. Instruments must be built to withstand impacts with dust, travelling at tens of kilometres per second. Electronics must endure the constant bombardment of cosmic rays. The Voyagers are already in this environment, their signals carrying back information about what lies above and below, confirming that interstellar space is not featureless but textured, filled with the quiet presence of matter. As we imagine the solar system drifting through this medium, it is useful to remember the scale of time involved. The Sun takes hundreds of millions of years to orbit the galaxy. In that time, it will pass through many different regions of interstellar space. Some will be dense, others diffuse, some will be hot, others cold. Each one will press differently on the heliosphere, altering its size and shape. Each one will change the flow of cosmic rays into the solar system. Over geological timescales, these variations may even affect Earth's climate and the conditions for life. The interstellar medium above and below us is not just scenery. It is part of the environment in which our planet's story unfolds. And so, when we ask what lies beyond the solar bubble, the answer is these clouds, this medium, this thin but powerful fabric between the stars. It is not as empty as it seems. It is alive with atoms, dust, magnetic fields, shockwaves, and the seeds of new worlds. It is the material that fills the galaxy, the backdrop against which stars shine, and the source from which stars are born. Above us and below us, the interstellar medium stretches, vast and quiet, waiting to be explored. When we lift our gaze above the plane of the solar system, we are not only moving beyond the heliosphere or beyond the interstellar clouds immediately surrounding us, we are beginning to look outward into the structure of our home galaxy. The Milky Way is not just a band of light in the night sky. It is an enormous rotating disk of stars, gas and dust, bound together by gravity and surrounded by a faint halo of older stars and dark matter. The solar system is just one small part of this system, orbiting the galactic centre along with hundreds of billions of other stars. Above us lies not empty space, but the larger neighbourhood in which our Sun resides. The first step in picturing this neighbourhood is to place ourselves. Our solar system is located in a small spiral arm of the galaxy called the Orion Arm, sometimes called the Orion Spur. It is a minor structure compared to the grander spiral arms like Sagittarius and Perseus, but it is our local lane in the galactic highway. The Orion Arm lies between two larger arms, and contains a mixture of stars, nebulae and clusters. When we talk about the Milky Way's neighbourhood above us, we are really talking about what lies outside the thin disk of the arm in the direction of the galactic north. That is, we are looking above the crowded plane and into the regions that rise out of the disk. One of the first things we encounter in this direction is the galactic halo. The halo is a roughly spherical region surrounding the disk of the Milky Way. It contains older stars, many of them grouped into globular clusters, which are dense collections of tens of thousands or even millions of stars bound together by gravity. These clusters orbit the galaxy like bees around a hive, not confined to the disk but scattered above and below it. Looking above us, we find some of these clusters shining faintly, relics of an earlier era in the galaxy's history. They are among the oldest structures we can see, with ages of 10 to 13 billion years, nearly as old as the galaxy itself. Between the disk and the halo lies another layer, often called the thick disk. While the thin disk of the galaxy is where most of the younger stars and gas reside, the thick disk contains older stars, less concentrated but extending farther above and below the galactic plane. It is thought to be a remnant of the galaxy's early history, perhaps formed by mergers with smaller galaxies or by turbulent processes in the past. When we look above our solar system, part of what we are seeing is this thick disk. a population of stars that tells the story of how the Milky Way assembled itself over billions of years. The Milky Way's neighbourhood above us also includes streams of stars that are the remnants of past mergers. Our galaxy has not lived a quiet life. Over its long history, it has absorbed smaller galaxies, tearing them apart with gravity and mixing their stars into its own structure. Some of these mergers are complete, but others are still visible as faint streams or arcs of stars stretching across the sky. These streams cross above the galactic plane, evidence of past encounters. Studying them gives astronomers clues about how the Milky Way grew, how often it collided with others, and how those events shaped the stars we see today. Dark matter is another part of this neighbourhood, though it cannot be seen directly. It is believed to make up most of the mass of the galaxy, forming a vast halo that extends far above and below the disk. Though invisible, its gravity holds the stars together, keeping the galaxy from flying apart as it spins. Above us, dark matter is present just as much as below. It is a silent companion to everything we observe, shaping the motions of stars and clusters. Even though we cannot detect it with our eyes, it is an essential part of the galactic neighbourhood. When we look above the solar system, away from the crowded band of the Milky Way, the sky appears clearer. The dust and gas of the galactic plane block much of our view when we look along it. But above and below, the line of sight is less cluttered, giving us windows to observe distant galaxies beyond our own. These windows are precious to astronomers. They allow measurements of the cosmic microwave background radiation, the faint afterglow of the Big Bang, which would otherwise be obscured. They also allow surveys of galaxies in the larger universe, letting us place the Milky Way in context. In this sense, looking above is not just about our immediate neighbourhood, but about opening a path to the broader cosmos. Still, the neighbourhood itself is worth pausing on. Within a few thousand light-years above us are a variety of star clusters, both open and globular. Open clusters are groups of young stars born from the same cloud of gas. They are less tightly bound than globular clusters, and often disperse over time. Many open clusters are found in the thin disk, but some extend above it, giving us a chance to see young populations in higher orbits. Globular clusters, by contrast, are ancient. Their stars metal poor, meaning they contain fewer heavy elements. These clusters are fossils of the galaxy's earliest days, and above us many can be found, orbiting quietly, shining faintly, marking the halo. Gas also extends into this region. Though most of the galaxy's gas lies in the disk, there are fountains of hot gas that rise above it. These are driven by supernova explosions and stellar winds that push material upward, out of the plane. The gas cools and eventually falls back down, cycling through the galaxy in a process called the galactic fountain. This means that above our solar system there is not just old, quiet structure, but also active flows of matter, rising and falling as part of the life cycle of the galaxy. The Milky Way's neighbourhood above us is also home to high-velocity clouds. These are large concentrations of gas moving at speeds different from the rotation of the disk. Some may be remnants of dwarf galaxies being absorbed. Others may be gas falling into the Milky Way from intergalactic space. Their origins are still studied, but they are important because they may provide fresh material to fuel future star formation. Above the disk, these clouds are more easily seen, drifting against the backdrop of the halo. Another part of the neighbourhood is the warp of the galaxy itself. The Milky Way's disk is not perfectly flat. It bends, rising on one side and dipping on the other, like a ripple frozen into place. This warp is thought to be caused by gravitational interactions with satellite galaxies or with the dark matter halo. When we look above the solar system, we are seeing part of this warped structure, a reminder that the galaxy is not rigid but shaped by ongoing forces. Nearby galaxies are also part of our broader neighbourhood. Above us, in the direction of the galactic north, lie some of the Milky Way's companions, dwarf galaxies that orbit it. These include systems like the Draco and Ursa Minor dwarfs, faint collections of stars bound loosely to our galaxy. Though small compared to the Milky Way, they are important. They show how galaxies interact, how they feed one another, and how stars can be stripped and added. These companions are part of the environment above and below us, satellites in the larger dance of the galaxy. All of these structures together make up the Milky Way's neighbourhood above us. It is not just stars scattered randomly, but layers of history and processes. The thick disk with its older stars, the halo with its ancient clusters, the streams of past mergers, the fountains of gas, the dark matter halo, the dwarf galaxies. Each one tells a piece of the story. Each one reminds us that the galaxy is alive, dynamic, and always changing. When we think about our place in this neighbourhood, it can feel vast beyond comprehension. But just as neighbourhoods on Earth give us a sense of belonging, this galactic neighbourhood can too. We are not drifting alone. We are part of a structure with history, with companions, with processes that tie us to the larger whole. Above us lies this community of stars, clusters and clouds, stretching far beyond what our eyes can see, but real nonetheless. When we think about what moves through the galaxy, it is easy to imagine stars and planets orbiting slowly, clouds of gas drifting across light years, and galaxies themselves colliding over cosmic timescales. But there is another kind of movement that is faster, more energetic and more subtle. The galaxy is threaded with highways that are not made of roads or paths, but of particles and winds. These highways carry some of the most powerful travellers in the cosmos, cosmic rays and stellar winds. Above us, below us, and in every direction, these flows move constantly, unseen but always present. Cosmic rays are high-energy particles, mostly protons and atomic nuclei, that travel at nearly the speed of the light. They are born in violent places. Some come from the explosions of massive stars, supernovae that hurl out shockwaves strong enough to accelerate particles to incredible speeds. Others may come from even more extreme environments, such as the regions around black holes or neutron stars, where magnetic fields twist and fling matter outward. Once accelerated, these particles do not slow down easily. They race through the galaxy, scattering off magnetic fields, changing direction but rarely stopping. Despite their name, cosmic rays are not rays of light but particles. They arrive at Earth constantly, striking the atmosphere and creating showers of secondary particles. Every second, your body is being hit by a small number of them, harmless at this level but a reminder that they are always present. High in the atmosphere and in space, the flux is stronger, and this is one reason why astronauts and satellites must contend with radiation. The heliosphere shields us from many of them, but not all. Some penetrate, depending on the state of the solar wind and the structure of the cocoon around us. Above and below the solar system, cosmic rays flow in, part of the galactic environment we live in. What makes cosmic rays particularly interesting is that they are a record of the galaxy's most energetic events. By studying their composition, scientists can learn what processes created them. Some carry signatures of elements forged in supernovae. Others may tell us about environments near pulsars or black holes. Their paths are twisted by magnetic fields, so tracing them back to their sources is difficult, but their presence itself is a constant reminder that the galaxy is an active, dynamic place. Above us, beyond the quiet appearance of the night sky, there are accelerators of unimaginable power, and cosmic rays are the messengers that reach us. Alongside cosmic rays there are stellar winds, the steady flows of particles from stars. Our Sun produces one, the solar wind, which shapes the heliosphere. Other stars produce similar winds, though the strength varies. Young hot stars often have stronger winds, shedding mass at high rates. These winds interact with the interstellar medium, carving out bubbles, creating shocks, and mixing material into the galaxy. Together, stellar winds from billions of stars form a kind of circulation system for the Milky Way, moving matter and energy across great distances. When many stellar winds and supernovae combine, they can create superbubbles, vast cavities in the interstellar medium filled with hot, low-density gas. These superbubbles can span hundreds of light years, bounded by shells of compressed gas. They're like neighbourhoods where the combined activity of many stars has reshaped the environment. The local bubble, the region our solar system currently resides in, is thought to be one such structure, created by multiple supernovae over millions of years. Above us, the edges of this bubble can be traced, showing where shockwaves and winds have carved out space. Cosmic rays and stellar winds are not independent. They interact with each other and with the galaxy's magnetic fields. The Milky Way is filled with magnetic field lines that twist and loop, shaped by rotation, turbulence, and the flows of matter. These fields act like guides for charged particles, bending their paths, trapping some, accelerating others. In this way, the galaxy has invisible highways, networks of magnetic lines along which particles stream. Cosmic rays, instead of travelling in straight lines, follow these winding routes, turning the galaxy into a web of hidden roads. Above the solar system, below it, these highways extend, always shifting but always present. One of the striking features of cosmic rays is their energy. Some have energies far beyond what we can achieve with human-built accelerators. The most energetic cosmic rays carry as much kinetic energy as a well-thrown baseball, concentrated into a single atomic nucleus travelling near light speed. When such a particle strikes Earth's atmosphere, it triggers a cascade of secondary particles, a shower that can spread over many kilometres. Detecting and studying these rare, high-energy rays is one of the great challenges of astrophysics. They tell us about the most extreme processes in the universe, processes powerful enough to fling matter across galaxies. The presence of these cosmic highways also raises questions about life and habitability. High levels of cosmic rays can be harmful, damaging DNA and eroding atmospheres. Planets without magnetic fields or thick atmospheres are especially vulnerable. The shielding provided by a heliosphere, like our own, may therefore be essential for life. Above us and below us, the galaxy's highways of radiation are always active, but our cocoon gives us safety from the worst of it. This makes our position within the galaxy and our protective layers part of the story of why Earth has remained habitable for billions of years. Cosmic rays are also part of the cycle of matter in the galaxy. When they collide with interstellar atoms, they can create new elements through processes called spallation. For example, elements like lithium, beryllium, and boron, which are rare from stellar fusion, are produced in part by cosmic ray collisions. This means that the highways of high-energy particles are not just dangerous, they also contribute to the chemical enrichment of the galaxy. Above us, invisible streams of particles are helping to shape the very inventory of elements available for future stars and planets. Stellar winds add another layer to this cycle. By blowing matter away from stars, they return gas to the interstellar medium. Over time, this recycled material mixes, cools, and can form new generations of stars. Winds from massive stars are especially important because they are enriched with heavy elements formed in the stellar cores. These winds seed the galaxy with the ingredients for planets and life. The circulation of winds, combined with the scattering of cosmic rays, is one way the galaxy renews itself, keeping the cycle of creation ongoing. When we picture the galaxy in this way, it is no longer a static collection of stars, but a dynamic system filled with movement. Above us, streams of particles cross light years in fractions of a heartbeat. Winds push outward from stars, colliding and merging with others. Shock waves carve out cavities. Magnetic fields weave paths through the chaos. The galaxy is alive with motion, not visible to our eyes but constant in its activity. On Earth we sometimes imagine the sky as calm, with stars shining steadily, unchanging. But the truth is that the space above us is buzzing with these invisible highways. Every second, cosmic rays reach us from across the galaxy. Every second, the solar wind carries particles away from our star. Every second, stellar winds from other suns mix into the medium. The stillness of the night sky is an illusion created by distance. Beneath it lies a ceaseless motion of energy and matter. highways of the cosmos weaving around us. Thinking of the galaxy this way changes our sense of place. We are not simply sitting in a quiet corner of space. We are part of a system in constant circulation, connected to distant stars by the particles they send out, connected to ancient explosions by the rays they produced, connected to the larger cycle of matter by the winds that carry it. Above and below, we are part of this flow, sheltered within our heliosphere but still immersed in the larger traffic of the galaxy. When we imagine our galaxy, it is easiest to picture it as a great disk. Stars, gas and dust are gathered into a wide but thin shape, turning slowly around its centre. From within the disk where we live, most of what we see are the crowded lanes of the Milky Way stretching across the night sky. But there is a special direction that takes us straight out of this crowded plane, like stepping through a doorway into clearer space. That direction is what astronomers call the North Galactic Pole. To look that way is to gaze directly above the disk, into a thinner region of stars, and beyond them into the wider universe. The galactic coordinate system is designed to give us this orientation. Just as Earth has a north and south pole, defined by its rotation, the galaxy has poles defined by the plane of its disk. The North Galactic Pole is the point on the sky that lies directly perpendicular to this plane. If you could stand far above the Milky Way and look down at its flat disk, that point would be directly overhead. From our perspective on Earth, the North Galactic Pole is located in the constellation Coma Berenices, a faint patch of sky that may not stand out at first glance but carries this special meaning. Looking toward this direction is not like looking into the band of the Milky Way. The band is rich with stars, bright with gas clouds, cut through with dark dust lanes. It is dazzling but crowded. The North Galactic Pole, by contrast, is a region of relative quiet. The density of stars is lower because we are looking out of the disk rather than along it. The dust that often obscures our view is also less of a problem. The result is a cleaner window into what lies beyond our galaxy. Above us, in this direction, the view opens outward into the universe. One of the remarkable things about the North Galactic Pole is that it allows astronomers to study distant galaxies with less interference. Surveys of galaxies beyond the Milky Way often focus on this region because the line of sight is not blocked by our own galactic plane. When telescopes peer in this direction, they can collect light from galaxies millions or billions of light years away. Instead of being hidden by the fog of our own stars, these distant systems can be seen clearly, letting us map the large-scale structure of the universe. In this way, looking above is like lifting a curtain and finding a whole stage behind it. The North Galactic Pole is also a region where the cosmic microwave background, the faint afterglow of the Big Bang, can be studied with less obstruction. This radiation fills the universe, but in the direction of the galactic plane, it is harder to detect cleanly because of the emission from stars and dust. Toward the galactic pole, the signal is clearer. This makes it one of the key vantage points for cosmology, the study of the universe as a whole. Above us through this window, scientists can glimpse not only other galaxies, but also the earliest light in the cosmos. The region around the North Galactic Pole is not completely empty. It contains galaxies of its own, including members of the Coma Cluster, a massive collection of thousands of galaxies bound together by gravity. The Coma Cluster lies more than 300 million light-years away, yet its presence is detectable in this direction. This cluster is one of the great structures in the nearby universe, and to look above us toward the galactic pole is to look in its direction. Beyond that cluster lie even more galaxies, stretching into the cosmic web that makes up the large-scale structure of the universe. When we think of what lies above the solar system, it is easy to focus on the immediate surroundings, the heliosphere, the interstellar medium, the local stars. But the North Galactic Pole reminds us that above is also a path outward, a line of sight that takes us far beyond the Milky Way. It is not just about our galaxy structure, but about the universe beyond. Above us, the North Pole of the galaxy opens a window that lets us see farther, study more deeply, and connect our local neighbourhood to the broader cosmos. Looking in this direction also highlights the difference between the disk and the halo of the galaxy. The halo, as mentioned before, is a roughly spherical region of older stars and globular clusters that surrounds the disk. When we look toward the North Galactic Pole, we are seeing through this halo. We may encounter faint clusters, ancient stars orbiting high above the disk, but beyond them the view is clearer. This gives astronomers a chance to study the halo itself, its composition, and its role in the galaxy. Above us in this way, the North Galactic Pole is both a path through the halo and a window beyond it. The North Galactic Pole also helps us understand perspective. On Earth, we are used to orienting ourselves by north and south, east and west, up and down. These directions make sense because we live on a sphere under the pull of gravity. In the galaxy, orientation is less intuitive. But by defining a galactic north, astronomers create a way to map the sky, to give ourselves bearings, to know where we are pointing. When we say we are looking above, we mean this specific direction, aligned with the North Galactic Pole. It is a human framework, but it gives us a handle on the vastness of space. The idea of looking above also ties into the motion of the solar system. As the Sun orbits the galactic centre, it does not stay perfectly within the disk. It oscillates, rising above the plane, then dipping below it, over tens of millions of years. This bobbing motion means that sometimes we're closer to the North Galactic Pole, sometimes farther. Over long timescales, our vantage point shifts, changing the angle of our view. The North Pole remains the same direction, but our relationship to it changes, adding another layer of motion to our place in the galaxy. The study of the North Galactic Pole has also revealed much about dark matter. By observing the motions of stars and clusters in this direction, astronomers can infer the presence of unseen mass. The halo of dark matter extends well above and below the disk, and looking toward the pole gives us one of the best views into how it shapes the galaxy. Though we cannot see dark matter directly, its gravitational pull is evident in the way stars move. Above us, in the quiet direction of the pole, this influence is especially clear. Thinking about the North Galactic Pole can also change the way we see the night sky. The stars we notice most easily are those along the band of the Milky Way, bright and numerous. But when we lift our gaze away from that band, into the darker, quieter regions, we are looking toward the pole. The fewer stars may make the view seem less striking, but in reality it is one of the most profound directions to look. Beyond those few stars lies an open window into the deepest parts of the universe. Above us, in the quiet sky, lies the path outward. And so, when we talk about what lies above our solar system, the North Galactic Pole is one of the clearest answers. It is not a place we can travel to, but a direction, a line of sight that takes us straight out of the disk through the halo and into the universe beyond. It is a reminder that above is not just about local structure, but about perspective, about the way we orient ourselves in space, about the way we connect our small part of the galaxy to the larger whole. When we think about what fills the space above our solar system, it is natural to picture stars, clouds of gas, and distant galaxies. These are things we can see, measure, and map with light. But there is something else that fills those regions, something invisible yet far more abundant. Astronomers call it dark matter. It does not shine, it does not reflect, and it does not interact with light in any way that we know. Yet its gravity shapes the galaxy, holds stars in orbit, and forms a halo around the Milky Way that extends far above and below the disk. When we ask what lingers above us, part of the answer is this unseen presence. The need for dark matter arises from simple observations. When astronomers measure the rotation of galaxies, they find that stars far from the centre move much faster than expected. If only the visible matter were present, the outer stars would orbit more slowly, just as planets far from the Sun move more slowly. But instead, Galaxies rotate almost like solid disks, with outer stars moving nearly as fast as inner ones. The only explanation that fits is that there is much more mass present than what we can see. That extra mass does not emit light, so it is called dark matter. In our own galaxy, dark matter is thought to outweigh visible matter by about 5 to 1. The stars, gas and dust that we can detect are only a small fraction of the total. The rest forms an extended halo that reaches far above and below the galactic plane. This halo is not dense like the disk. Instead, it is diffuse, spreading over hundreds of thousands of light years. But its gravity is strong enough to hold the galaxy together, to prevent the stars from flying apart as they orbit the centre. Above us, the halo stretches silently, its particles unknown, but its influence unmistakable. One way to picture this halo is to imagine the Milky Way as a thin disk of light, floating inside a much larger invisible sphere. The disk is what we see in the night sky, the band of stars and nebulae. The sphere is the dark matter halo, unseen but enveloping everything. The solar system, orbiting within the disk, is also orbiting within this halo. So when we look above, beyond the thin layers of stars and into the darker regions, we are looking into the volume where dark matter dominates. Astronomers have tried many ways to detect dark matter directly, but so far it has remained elusive. Experiments deep underground, designed to shield out cosmic rays, wait for the faintest signal of a dark matter particle colliding with an atom. Telescopes look for hints of dark matter interactions in cosmic rays or gamma rays. Particle accelerators search for new particles that could explain it. None of these searches have yet provided a definitive answer, and yet the evidence for dark matter's existence from gravity is overwhelming. Above us, though unseen, it is there. It bends the paths of stars, it curves the light of galaxies beyond, it lingers in every direction. The halo of dark matter is not uniform. Simulations suggest it may be clumpy, with denser regions and streams left over from the mergers of smaller galaxies. As the Milky Way absorbed these galaxies, their dark matter was added to the halo, leaving trails that still circulate today. Some of these streams may pass close to the solar system, bringing slightly higher densities of dark matter through our neighbourhood. If so, then above us and below us, these invisible rivers flow, part of the galaxy's hidden structure. Gravitational lensing provides another way to see dark matter indirectly. When light from a distant galaxy passes near a massive object, its path bends, much like light through a lens. By measuring this bending, astronomers can map the distribution of mass, even if the mass is dark. Large surveys of galaxies have shown that halos of dark matter are common, surrounding not only the Milky Way but every galaxy. Above us, the space that looks so empty is in truth filled with this unseen scaffolding. Dark matter also plays a role in the formation of galaxies themselves. In the early universe, before stars and galaxies existed, dark matter began to clump under its own gravity. These clumps attracted gas, which cooled and formed the first stars. Without dark matter, galaxies might never have formed. It is the framework on which the visible universe is built. Above our solar system, beyond the stars we can see, this framework remains, holding the galaxy together. The nature of dark matter is still one of the greatest mysteries in science. Some theories propose it is made of weakly interacting massive particles, or WIMPs. Others suggest lighter particles called axions. Some explore more exotic possibilities, such as modifications to gravity itself. Whatever the answer, the evidence is clear that something unseen is present. Above and below us, this something outweighs everything we can see, shaping the galaxy we call home. The search for dark matter is not only about physics, but also about perspective. It reminds us that what we see is only a fraction of reality. The bright stars, the glowing nebulae, the shining galaxies are like the tip of an iceberg. Most of the mass lies hidden, silent, invisible. Above us, what lingers is not just light but shadow. Not just matter we can touch, but matter we cannot. The universe is more than it appears, and dark matter is the largest part of that unseen whole. If we could somehow see dark matter, the night sky would look very different. The band of the Milky Way would still be there, but it would be embedded in a vast, faintly glowing halo stretching far above and below. Streams and clumps would arc across the sky, remnants of galaxies long since merged. The stars we know would be embedded in a much larger structure, reminding us that light is only part of the story. Above us, the invisible dominates. The influence of dark matter extends even farther than the Milky Way. Our galaxy is part of a group of galaxies called the Local Group, which includes Andromeda and many smaller companions. These galaxies are bound together by their combined gravity, much of it from dark matter. The halos of the Milky Way and Andromeda may even overlap. Above us, in the space between galaxies, dark matter fills the void, binding the group together. Even larger structures such as galaxy clusters and superclusters are dominated by dark matter. The Coma cluster, mentioned before, contains thousands of galaxies, but far more dark matter than visible matter. These clusters are held together not by the light of their stars, but by the gravity of their unseen mass. Above us, beyond the Milky Way, these immense halos stretch, linking galaxies into the cosmic web. When we ask where dark matter lingers above us, the answer is everywhere. It lingers in the halo of our galaxy, in the streams of past mergers, in the local group, in the clusters beyond. It lingers in every direction, unseen but shaping everything. Its presence is constant, its influence undeniable, even if its nature remains hidden. For now, dark matter is a mystery we live inside. We cannot touch it, we cannot see it, yet we are surrounded by it. Above and below, within the halo, through the disk, beyond the stars, it is always there. It lingers quietly, waiting for us to understand, waiting for the day when we can say not only that it exists, but also what it is. When we think of the galaxy, our minds naturally go first to the bright disk, the familiar band of stars stretching across the night sky. That disk is where the majority of stars live, where gas and dust gather, where spiral arms curl outward. But surrounding this disk is something quieter, older and more mysterious. It is the galactic halo, a vast spherical region that extends far above and below the plane of the Milky Way. To peek into the halo is to step beyond the crowded lanes of the disk and into the outskirts of the galaxy, where the traces of its earliest history linger. The halo does not shine brightly. It is not filled with thick bands of stars like the disk. Instead, its stars are scattered, sparse, and ancient. Many of them are found in globular clusters, dense balls of stars bound tightly by gravity. These clusters contain some of the oldest stars in the galaxy, with ages stretching back more than 10 billion years. They are fossils of the galaxy's youth, remnants from the time when it first formed. When we look above the disk, toward the halo, we are looking at stars that have witnessed almost the entire history of the Milky Way. Globular clusters are striking in their own way. Each one contains tens of thousands, sometimes hundreds of thousands, of stars packed into a relatively small volume. Seen through a telescope, they appear as brilliant spheres of light, with stars so densely crowded that they almost blur together. They orbit the galaxy in wide elliptical paths, often far above or below the disk. Their distribution forms part of the halo surrounding the Milky Way like satellites. To peek into the halo is to see these ancient clusters shining faintly, reminders of how long the galaxy has endured. But the halo is more than just globular clusters. It also contains individual stars, many of which are metal poor, meaning they contain very few elements heavier than hydrogen and helium. This is another sign of their age. The first generations of stars were made almost entirely of these light elements, and only later, as stars lived and died, were heavier elements added to the mix. halo stars often have a chemical makeup that reflects this early era, making them valuable records of the past. Above us, scattered through the halo, these stars drift slowly in wide orbits, carrying within them the fingerprints of the early universe. The halo also bears the scars of galactic mergers. Over its long life, the Milky Way has absorbed many smaller galaxies, pulling them apart with gravity and adding their stars to its own. The remnants of these mergers are still visible as streams of stars, long, thin arcs stretching across the halo. These streams trace the paths of dwarf galaxies that once orbited the Milky Way, slowly torn apart and spread out. Astronomers have identified several such streams, including the Sagittarius stream, which is the remnant of a dwarf galaxy still in the process of merging with us. When we look into the halo, we see these threads of stars, evidence of the galaxy's ongoing growth. Dark matter is thought to dominate the halo as well. While the visible stars and clusters are only a small part of its mass, the larger portion is the unseen matter that holds the galaxy together. The halo extends much farther than the disk, reaching out hundreds of thousands of light years, enveloping not just the Milky Way but also influencing its neighbours in the local group. Above us, beyond the stars we can see, this dark matter halo stretches silently, shaping the motions of everything within it. Peeking into the halo also gives us a different view of the galaxy's structure. The disk is thin, only a few thousand light-years thick, compared to its 100,000 light-year diameter. The halo, by contrast, is spherical, surrounding the disk in all directions. When we look above, we are looking through this sphere, seeing not only the stars that belong to it, but also the space it occupies. It is a reminder that the galaxy is not only a flat spiral, but a three-dimensional system with layers extending far beyond what we see with the naked eye. The halo is not uniform. It contains substructures, streams and clumps that reveal its history. Some of these features are the remains of dwarf galaxies, others are shells of stars from past mergers. By mapping them, astronomers can reconstruct the Milky Way's past, learning how many galaxies it has consumed, when the mergers happened, and how they shape the present structure. Above us, these faint features are like fingerprints left by past events, written across the halo. The gas in the halo is another important part of the story. While the disk contains dense gas clouds where stars form, the halo contains hot, diffuse gas that stretches far outward. This gas is difficult to detect directly, but it can be studied through the absorption lines it leaves in the light from distant quasars. Observations suggest that the halo contains as much gas as the disk, though spread much more thinly. This reservoir of gas may help sustain star formation in the galaxy by slowly feeding the disk over time. Above the solar system, this halo gas extends, invisible but crucial to the life of the Milky Way. The halo also connects us to the larger structures beyond the galaxy. Many of the dwarf galaxies that orbit the Milky Way move within the halo. The large and small Magellanic Clouds visible in the southern sky are two such companions. Their orbits, interactions, and eventual fate are shaped by the dark matter halo. Streams of gas, like the Magellanic Stream, trail behind them, feeding into the halo and the disk. When we look above, peeking into the halo, we're seeing not only the remnants of past mergers, but also the ongoing interactions that will shape the galaxy's future. Peering into the halo is like looking into the memory of the Milky Way. Its stars are old, its clusters ancient, its streams the remnants of long-gone galaxies. Its gas is a reservoir for future star formation. Its dark matter is the unseen skeleton that holds it together. Above and below us, the halo is always there, quiet, extended, and essential. Without it, the Milky Way would not be what it is. And so, when we look beyond the disk and lift our gaze into the darker parts of the sky, we are peeking into this halo. It may not dazzle like the spiral arms, but it is just as important, perhaps more so. It tells us where we came from, how the galaxy grew, and what structures surround us even now. Above us, the halo stretches, vast and faint, holding within it the history and the future of the Milky Way. When we speak about what lies above and below our solar system, we need to begin by knowing what above and below really mean. In space, there is no ceiling or floor. There is no natural up or down. What astronomers do instead is create a reference, a framework that lets them define direction in a consistent way. For the solar system, that reference is the ecliptic plane. It is the invisible surface traced out by the orbit of Earth around the Sun, extended across space as a kind of baseline. From this baseline we can say what lies north, what lies south, and by extension what lies above and what lies below. The ecliptic plane is not just a convenient tool, it is a reflection of the way the solar system formed. Billions of years ago, when the Sun and planets were still condensing out of a rotating disk of gas and dust, the spin of that disk set the pattern for the orbits. Most of the material flattened into the same general plane, and from that disk the planets were born. This is why nearly all of them orbit in roughly the same flat sheet of space. Mercury tilts a little, Pluto tilts a lot, but on the whole, the planets line up within a few degrees of one another. The ecliptic plane is the remnant of that primordial disk, frozen into the geometry of the solar system. Because Earth's orbit defines this plane, the Sun appears to follow it in the sky. Over the course of a year, as Earth makes its circuit, the Sun seems to move along a path relative to the background stars. This path is the ecliptic, and it is why the constellations of the zodiac all lie along the same line. The Moon and planets also follow this general path, since their orbits are close to the same plane. If you look up on a clear night and see several planets strung across the sky, you're seeing the trace of the ecliptic, the invisible map that ties their motions together. This invisible map also gives us orientation for the solar system as a whole. If you extend a line perpendicular to the ecliptic, it points toward what astronomers call the north ecliptic pole. The opposite direction points toward the south ecliptic pole. With this framework, we can talk about above and below the plane, knowing what directions we mean. It is a human construct, but it reflects real physics, the actual flattening of orbits into a disk. Above us means toward the north side of the ecliptic. Below us means toward the south. The ecliptic plane also helps us understand the distribution of smaller bodies in the solar system. The asteroid belt lying between Mars and Jupiter is spread mostly along the plane. The Kuiper belt beyond Neptune also aligns with it. Even the distant scattered disk of icy objects follows this general orientation. These belts and disks are like faint shadows of the original formation process, still clinging to the same flattened shape. Above and below the plane, far fewer objects are found. The majority of the solar system's matter remains tied to this invisible sheet. One of the interesting things about the ecliptic is that it defines not only the motion of planets, but also the way we measure the sky. Astronomers use it as a coordinate system, mapping the positions of stars and galaxies relative to the plane of Earth's orbit. Just as sailors once used latitude and longitude to navigate the seas, astronomers use ecliptic coordinates to navigate the sky. This invisible grid allows precise measurements, linking Earth's motion to the larger universe. Above us and below us in this framework have clear meanings tied to our own orbit. The inclination of planetary orbits adds subtle variation to this map. Mercury, for example, is tilted about 7 degrees relative to the ecliptic. Pluto is tilted about 17 degrees. These differences mean that sometimes planets and smaller bodies wander slightly above or below the invisible sheet. Over time, their paths cross back and forth. The ecliptic remains the baseline, but the dance of orbits adds texture, a gentle wavering that reflects the complexity of gravity's pull. Looking above the plane, we can find these wanderers rising briefly before dipping back down. Comets add even more variety. Many of them come from the Oort cloud, a spherical shell of icy bodies far beyond the planets. When they are nudged inward, their orbits can be tilted at any angle, cutting across the ecliptic in dramatic paths. These visitors remind us that while the ecliptic defines the dominant structure, it is not the only one. Above and below, far beyond the plane, objects exist with their own orientations, their own histories. The invisible map is strong, but it does not bind everything. The ecliptic plane is not fixed against the backdrop of the galaxy. It slowly shifts due to gravitational influences, a process called precession. Over tens of thousands of years, the orientation of the plane changes slightly, altering the position of the ecliptic poles. This long, slow movement is another reminder that even the frameworks we create are not eternal. The invisible map of orbits is steady on human timescales, but on cosmic ones it drifts, influenced by the subtle pull of other planets and the larger forces of the galaxy. Above and below the plane, astronomers find interesting differences in perspective. When looking above, toward the north ecliptic pole, we're gazing into a region of the sky away from the galactic centre, giving us a clearer view of distant galaxies. When looking below, toward the south ecliptic pole, we see a slightly different slice of the universe. These directions are important for planning observations, for choosing windows in which to study the cosmos beyond our solar system. The ecliptic plane is not just a local reference, but a tool that connects our orbit to the wider universe. The invisible map of orbits also plays a role in how spacecraft are launched and navigated. Missions to other planets are often planned along the ecliptic because that is where the planets travel. Launching outside this plane requires more energy, making missions less efficient. As a result, the ecliptic is not just an abstract reference, but a practical one. Above and below the plane, spacecraft rarely venture unless there is a specific reason. The majority of exploration remains tied to this flattened sheet, the same sheet that has guided planetary motion since the beginning. If you could see the solar system from far away, looking down on it from above the ecliptic, it would appear as a series of nested circles, each planet tracing its path around the sun. The asteroid belt would appear as a rough band. The Kuiper belt would form a broader ring. Comets and tilted objects would be the exceptions, cutting across at odd angles. From this perspective, the invisible map becomes visible, the logic of the plane clear. The flattening is striking, the order undeniable. The solar system is not a random scatter, but a disk, with the ecliptic at its core. Thinking about the ecliptic plane is a reminder that even in the vast openness of space, there are patterns, structures, and frameworks that give order to motion. The planets are not drifting aimlessly. They are bound to this shared sheet, a relic of their origin. Above and below the plane, exceptions exist, but the majority remain faithful to the map. For astronomers, for explorers, for anyone who wants to understand where we are and how we move, the ecliptic plane is essential. And so, as we imagine what lies above and below the solar system, we must picture this invisible map first. It is the baseline, the reference, the foundation of orientation. It ties the motions of planets, asteroids, and comets into a coherent whole. It connects Earth's orbit to the rest of the solar system, and, by extension, to the galaxy beyond. Above us and below us, everything is relative to this plane. It is the quiet framework beneath the dance of orbits, the unseen but ever-present sheet that guides the paths of worlds. When we spoke about looking above the galactic disk, we found ourselves drawn toward the North Galactic Pole, a direction that offers one of the clearest windows out of our galaxy. But just as there is a north, there is also a south. The South Galactic Pole lies in the opposite direction, straight beneath the disk, away from the crowded plain of the Milky Way. To look that way is to gaze down through the halo, past the thin band of stars and into the same wider universe, but from the opposite side of the disk. Together these two poles define what it means to look directly out of our galaxy, one upward, one downward, each giving us a perspective that complements the other. The South Galactic Pole is located in the constellation Sculptor. Unlike some of the brighter, more familiar constellations, Sculptor is faint, composed of modest stars that don't immediately stand out. But in terms of direction, it carries enormous importance. If you were to draw a line straight down from the plane of the Milky Way, Continuing beyond the faint haze of dust and stars, it would point directly at this pole. For astronomers, it is as essential a marker as the celestial poles on Earth. It is the southward counterpart of the window above, a path that points straight out of the disk into clearer space. Looking toward this direction has many of the same advantages as looking toward the North Pole. The thick dust and gas that obscure so much of the sky when we look along the Milky Way are largely absent here. The density of stars is lower, so the view is cleaner. This means that observations of the distant universe are easier. Surveys of galaxies, cosmic background radiation, and large-scale structures often focus on the regions around both poles, because they provide unobstructed paths. Above us we found one such window. Beneath us lies its mirror, offering a complementary field of view. The Sculptor region is notable for another reason. It contains the Sculptor group of galaxies, one of the nearest collections of galaxies outside our local group. This group lies about 10 to 12 million light-years away, and includes galaxies such as NGC 253, often called the Sculptor galaxy. This particular galaxy is one of the brightest spiral galaxies in the sky, and a starburst galaxy, meaning it is undergoing a high rate of star formation. To look beneath the galactic disk toward the South Pole is to look into the region of space where these galaxies reside, giving us a glimpse of structures just beyond our immediate neighbourhood. The Sculptor galaxy itself is striking when seen through telescopes. It is tilted at an angle that shows us its disk clearly, a band of light rich with dust lanes and clusters. Within it, stars are being born at a rapid pace, lighting up the galaxy with new energy. When we gaze toward the South Galactic Pole, we are not only looking outward into emptier space, but also directly at this region, where the nearest group of galaxies beyond our own is actively shaping itself. It is a reminder that beneath the disk lies not just quiet emptiness, but the lively activity of other stellar systems. The South Galactic Pole also serves as a vantage point for studying the cosmic microwave background. This faint glow of radiation, left over from the Big Bang, is spread evenly across the sky, but it is easiest to measure where the Milky Way does not interfere. Both galactic poles offer these clean windows. Instruments like the Planck satellite and the Wilkinson microwave anisotropy probe relied on observations through these windows to map the subtle variations in the cosmic background. These variations are the fingerprints of the universe's earlier structure, and they can be studied more clearly when looking away from the galactic plane. Beneath the disk, the South Pole provides such a path. Just as the halo of the galaxy stretches above us, it stretches below us as well. When we gaze toward the South Pole, we are looking through the same spherical halo of stars, globular clusters, and dark matter that surrounds the Milky Way. Globular clusters in this region are visible, dense swarms of ancient stars that orbit the galaxy independently of the disk. Their ages, often exceeding 10 billion years, make them some of the most valuable relics of the galaxy's early history. Beneath the disk, in the direction of the South Pole, these clusters remind us that the galaxy's outskirts are filled with fossils of its formation. The halo also contains streams of stars, remnants of smaller galaxies that were absorbed by the Milky Way. Some of these streams pass through the southern sky, arcs of faint light that stretch across the halo. By mapping these streams, astronomers can reconstruct the mergers that built the galaxy, piecing together the history of its growth. When we peek toward the South Galactic Pole, part of what we are seeing is this archaeology of stars, faint traces of long-gone galaxies scattered beneath the disk. Dark matter extends in this direction as well. The unseen halo that holds the Milky Way together is just as present beneath us as it is above. Its gravity shapes the orbits of clusters and stars, binding them to the galaxy. Looking toward the South Pole, we're gazing into this unseen structure, the framework of matter that dominates our galaxy even if we cannot see it. Its presence is as real in the southern sky as in the northern. One of the subtle differences between the North and South Galactic poles lies in the specific galaxies and clusters that fall along the line of sight, While the North Pole gives us a clearer view of regions like the Coma Cluster, the South Pole opens the view to the Sculptor Group and other southern systems. Each direction provides not only a window out of the Milky Way, but also a path into a different part of the larger cosmic web. Beneath the disk, the southern path highlights structures in our near-cosmic neighbourhood that differ from those above, giving us a fuller picture when both are considered together. The South Galactic Pole also has cultural and observational significance for people in the southern hemisphere. While observers in the north may find the northern pole more directly overhead, those in the south can look towards Sculptor and its galaxies more directly. For astronomers in places like Chile, Australia and South Africa, the southern sky offers unique opportunities to study these regions. The clear, dry skies of high observatories in the Andes, for example, have been used to peer deeply into the Sculptor Group and beyond, taking advantage of the southern pole's window. The ecliptic and celestial poles of Earth add another layer to this view. Just as the Earth's north and south poles define our orientation on the planet, the galaxy's poles give us orientation in the cosmos. To look beneath the disk is to align ourselves with this framework, to know that we are looking straight out of the plane into clearer skies. It is a reminder that orientation matters even in space, where there is no true up or down. By defining directions like the South Galactic Pole, we give ourselves a consistent way to navigate the vastness. Beneath the disk, the stars are fewer, the dust is thinner, the view is wider. And yet, this direction is every bit as rich as the one above. The Sculptor Galaxy and its group lie there, nearby companions beyond the local group. Globular clusters and stellar streams fill the halo. Dark matter shapes everything silently. The cosmic microwave background shines through more cleanly. To gaze beneath the disk is to step outside the crowded band of the Milky Way, and into a broader perspective, one that links us to the universe beyond. And so, when we think about what lies below the solar system, one of the clearest answers is this direction, the South Galactic Pole. It is a path beneath the disk, through the halo, out into nearby galaxies, and onward into the cosmic web. It balances the view above, completing the symmetry of north and south. Together, these two directions remind us that above and below are not just words but windows, openings through which we can glimpse the wider universe. Far beyond the orbits of the planets, farther still than the Kuiper Belt and the scattered disk of icy bodies, lies a region so vast and so remote that it is more an idea than something we have directly observed. This region is called the Oort cloud, a spherical shell of icy fragments that is thought to surround the solar system like a faint and distant halo. When we ask what lies above and below, the Oort cloud provides one of the most striking answers. It is not confined to the flat plane of the ecliptic, but extends in all directions, forming a great shell that wraps the solar system on every side. The Oort cloud was first proposed in 1950 by the Dutch astronomer Jan Oort. He noticed that long-period comets, those with orbits lasting thousands or even millions of years, seemed to come from far beyond the known regions of the solar system. Their orbits were too elongated, too random to be explained by the Kuiper Belt or by interactions with the giant planets. Oort suggested that these comets originated in a vast reservoir of icy bodies surrounding the solar system at great distances. Whenever one of these distant objects was nudged by the gravity of a passing star or by the tidal forces of the Milky Way itself, it could be sent inward, falling toward the sun and appearing to us as a comet. The Oort cloud, though invisible, would explain the supply of these comets over billions of years. The distances involved are almost beyond comprehension. The inner edge of the Oort cloud is thought to begin around 2,000 astronomical units from the Sun, where 1 astronomical unit is the distance between Earth and the Sun. For comparison, Neptune orbits at about 30 astronomical units. The outer edge of the Oort cloud may extend as far as 100,000 astronomical units, nearly halfway to the next star. Light itself would take more than a year to cross such a distance. Above us and below us, this shell stretches unimaginably far. enclosing the solar system in a sphere of icy debris. The objects in the Oort cloud are believed to be remnants from the early solar system. When the planets formed, countless smaller bodies were scattered by their gravity. Some were ejected entirely, cast out into interstellar space. Others were thrown into distant orbits, too far to return but still bound to the Sun. Over time, these scattered objects settled into the Oort cloud, forming a great reservoir that persists to this day. Above and below, behind and ahead, they remain, drifting silently in the darkness, frozen relics of the time when the solar system was new. We have never seen the Oort cloud directly. Its objects are too small, too far, and too faint to detect with current telescopes. What we know comes from the comets that fall inward. Their orbits betray their origins, pointing back to the great sphere that surrounds us. Every bright comet that appears in the night sky, with a tail stretching across the stars, may be a messenger from the Oort cloud, a visitor from the frozen shell above and below us. Each one carries with it information about the conditions in the early solar system, preserved in ice and dust for billions of years. The Oort cloud is divided into two regions, the inner and the outer. The inner Oort cloud, sometimes called the Hills cloud, is a denser, closer region that may act as a buffer, feeding comets into the outer cloud. The outer Oort cloud is more diffuse, stretching to the farthest reaches of the Sun's gravitational influence. Together, these regions form the shimmering shell that wraps the solar system. Though invisible, the idea of it is powerful. Above the ecliptic, below it, in every direction, this cloud is thought to stretch, quiet, and cold. The gravitational environment of the Oort cloud is delicate. At such great distances, the Sun's pull is weak, and the influence of other stars becomes significant. Passing stars can tug on the orbits of Oort cloud objects, sending some inward and others outward. The tidal field of the Milky Way, the slow but steady stretching of gravity from the galaxy itself, also shapes the cloud. This means that above and below the solar system, the Oort cloud is not static. It is constantly perturbed, stirred gently by the galaxy, releasing comets into the inner system every so often. When these comets enter the solar system, they give us a glimpse of their origins. Their ices evaporate as they approach the Sun, forming bright comas and tails. The gases and dust they release carry chemical signatures that tell us about the environment in which they formed. Some comets contain molecules that may have played a role in the origin of life on Earth, delivering water and organic compounds in the planet's youth. In this way, the Oort cloud is not just a distant shell, but a source of material that has shaped our world. Above and below, the frozen bodies that drift in the cloud are part of the story of life itself. The number of objects in the Oort cloud is staggering. Estimates suggest there may be trillions of them, ranging from tiny icy fragments to bodies tens of kilometres across. They're spread over such a vast volume that the average distance between them is immense, but the total population is enormous. This makes the Oort cloud one of the largest structures associated with the solar system, not in terms of mass, but in terms of volume. Above us and below us, it stretches farther than any other part of our system, farther even than the heliosphere or the Kuiper belt. Thinking about the Oort cloud also changes the way we define the solar system. If we consider only the planets, the system ends with Neptune or Pluto. If we include the Kuiper belt, it stretches farther. But if we include the Oort cloud, the solar system extends halfway to the nearest star, overlapping with interstellar space. In this sense, the boundary between the solar system and the galaxy is blurred. Above and below us, the Oort cloud is both part of our system and part of the larger galactic environment, influenced by both the Sun and the stars beyond. The Oort cloud also connects us to the idea of interstellar visitors. In recent years, astronomers have detected objects passing through the solar system that appear to come from other stars, such as Oumuamua in 2017 and Borisov in 2019. These interstellar visitors may be similar to the objects in our own Oort cloud, ejected long ago from distant systems. Likewise, some of our Oort cloud objects may one day be ejected, becoming wanderers between the stars. In this way, the cloud is not only a shell, but also a bridge, linking our solar system to others through the exchange of icy fragments. Above and below, the Oort cloud remains unseen, but its influence is constant. It explains the origin of long-period comets. It carries the history of the early solar system. It interacts with the galaxy, feeding material inward. It blurs the boundary between our system and the stars beyond. Though we cannot see it, we know it is there, wrapping us in a shimmering shell of ancient ice. When we think about the Oort cloud, it is easy to imagine it as a silent shell, distant and almost abstract. But within that shell are countless individual worlds, small icy bodies that drift through the cold, waiting. Some of them will never move from their remote orbits. Others, over time, will be nudged by the faint tug of a passing star or the slow pull of the galaxy, shifting their paths until they fall inward. These are the comets, the long-period travellers that sometimes make their way into the inner solar system. They spend almost all of their existence in the deep below, far beyond the planets, in a place where sunlight is little more than a memory. A comet is essentially a mixture of ice, rock, and dust, a frozen remnant from the birth of the solar system. Unlike planets, which grew large enough to melt and differentiate into layered worlds, comets remained small. They preserved their primitive composition, unaltered for billions of years. Each one is a time capsule, a record of the materials that swirled in the disk of gas and dust that surrounded the young sun. While planets evolved, surfaces reshaped, and atmospheres changed, comets stayed simple, keeping within them the story of the early days. In the deep below, these comets are invisible. At distances of thousands or tens of thousands of astronomical units, they reflect almost no sunlight. Even if one were the size of a mountain, it would be fainter than our most sensitive telescopes could detect. They are, for all practical purposes, hidden. We know them only when they leave their slumber and come closer, when gravity draws them inward and the heat of the sun wakes them. Then they develop comas and tails, bright signatures that can stretch across the sky. But that bright passage is only the briefest fraction of their lives. For most of their existence, they are waiting in the deep. The triggers that send comets inward can be subtle. A nearby star passing within a few light years can alter the orbits of Oort cloud objects. The slow tidal forces of the Milky Way can shift them over millions of years. Even the accumulation of tiny gravitational tugs from planets and other bodies can have an effect. Eventually, some are nudged onto paths that carry them toward the sun. What to us appears as a sudden arrival of a comet is, in reality, the result of countless delicate influences acting over vast timescales. Above and below the solar system, this quiet stirring is always happening, slowly preparing the next cometary visitors. When a comet does approach, the transformation is dramatic. As it comes closer to the sun, its ices begin to sublimate, turning directly from solid to gas. This gas carries dust with it, forming a glowing coma around the nucleus. Solar radiation and the solar wind then stretch this material into tails, one made of dust and the other of charged particles. These tails always point away from the sun, curving across the sky as the comet moves. The sight is one of the most beautiful in astronomy, a fleeting visitor from the deep that announces itself with light and motion. But beneath that beauty lies fragility. Many comets break apart after repeated passages near the sun, their nuclei fragmenting into smaller pieces. Others fade as their volatile materials are exhausted, leaving behind only inert rocks. Each comet is on borrowed time once it enters the inner solar system. The deep below is where they can survive indefinitely, untouched, waiting for the rare chance to be disturbed. The brightness we see in the sky is the comet's farewell, the final act of an object that has spent billions of years in silence. Comets from the Oort cloud are distinct from those of the Kuiper belt. The Kuiper belt, lying just beyond Neptune, supplies shorter period comets with orbits measured in decades or centuries. The Oort cloud, by contrast, supplies long-period comets with orbits of thousands or millions of years. These long-period comets come from every direction, not confined to the ecliptic, because the Oort cloud is spherical. When one appears, it may come from above or below, from any point on the sky. It is a reminder that the solar system is not just a flat disk, but is surrounded by this spherical shell of icy remnants. The waiting comets in the deep below also play a role in shaping planets. In Earth's early history, comets are thought to have delivered much of its water. The isotopic composition of water in some comets matches that of Earth's oceans, suggesting a connection. Comets may also have delivered organic molecules, contributing to the chemistry that led to life. If so, then the long dormancy of these bodies was not wasted. They were storing the ingredients of habitability, waiting until the right nudges brought them inward. From the deep below, they may have played a part in making Earth what it is. The number of comets in the Oort cloud is vast. Estimates range into the trillions, a population so large that it dwarfs anything closer in. Most will never come inward. Most will remain frozen, drifting endlessly. But even if only a tiny fraction are disturbed, that is enough to supply the solar system with comets for billions of years. This is why we still see them today, long after the solar system's formation. The reservoir is immense, and it continues to feed the inner regions slowly, steadily, with visitors from the deep. When comets do fall inward, their orbits can take them astonishingly close to the Sun. Some graze the solar surface, disintegrating entirely in the heat. Others swing around and head back outward, destined not to return for thousands of years. These journeys show us just how vast their original orbits are. A comet visible in the sky tonight may not return until long after human civilization has changed beyond recognition, if it returns at all. Beneath the solar system, in the Oort cloud, countless others wait their turn, their paths unknown, their futures uncertain. Studying comets gives us one of the few direct connections to the Oort cloud. Space missions like Rosetta, which orbited and landed on comet 67P, Churyumov-Gerasimenko, and Stardust, which collected samples from a comet's coma, have revealed their structure in detail. These missions studied comets from the inner solar system, but they are representatives of the larger population that waits beyond. Each measurement, each analysis of dust and ice helps us understand what lies in the deep below. Even without direct access to the Oort cloud, comets carry its story inward for us to read. There is also the possibility that some comets are ejected entirely, leaving the solar system forever. If a passing star perturbs an orbit strongly enough, an object can be freed from the Sun's gravity, becoming an interstellar wanderer. In the same way, our solar system may capture comets from other stars, adding them to the Oort cloud. This exchange blurs the boundary between systems. The comets waiting in the deep below are not only our own. Some may be immigrants from elsewhere captured long ago, while others may one day leave to drift between the stars. Thinking about the comets in this way gives the Oort cloud a dynamic quality. It is not just a static shell, but a reservoir in motion, shaped by gravity, stirred by the galaxy, exchanging material with other systems. Above and below comets wait, not all destined to come inward, but all part of this vast potential. Their waiting is not lifeless, but meaningful, a readiness that connects the solar system to its history and to the wider galaxy. And so, when we picture the deep below, we should not imagine it as empty. It is filled with countless frozen travellers, each holding the story of the solar system's youth. They wait in silence, drifting in darkness, until the slow hand of gravity nudges them onto paths that carry them inward. From time to time one of them arrives, lighting up the sky with a glowing tail. But most remain where they are, hidden in the deep. Above and below they are always there, comets waiting for their turn to journey toward the light. When we talk about comets waiting in the deep below, we are thinking of objects that belong to the solar system, held loosely by the gravity of the Sun. But every so often something arrives that does not belong to our system at all. These are the interstellar visitors, bodies that formed around other stars and then were ejected, wandering through the galaxy until they happen to pass near us. When they appear, they often come from unexpected directions, cutting across the ecliptic at steep angles. Some of them arrive from beneath the plane of the solar system, travelling upward through our neighbourhood before continuing on their way. These visitors are reminders that the solar system is not an isolated island. It is connected to the larger galaxy by pathways of wandering objects, and some of those pathways lead from the deep below. The first such object confirmed by astronomers was detected in 2017. It was given the name Oumuamua, a Hawaiian word meaning scout, or messenger from afar arriving first. It moved too fast to be bound by the sun's gravity, and its trajectory showed it had come from interstellar space. Its path carried it through the inner solar system before swinging past the sun and heading out again. For a brief time, it was close enough to study, but it was already receding before we even knew it was there. Oumuamua's origin remains mysterious. Its shape, motion, and lack of a visible coma puzzled scientists. Some proposed it was an unusual kind of comet or asteroid. Others suggested more exotic explanations. Whatever it was clearly not born here. It had come from the galaxy, from somewhere beyond, passing through like a stranger on a long journey. 2 years later, in 2019, another interstellar object was discovered. This one was named Borisov, after the amateur astronomer who first spotted it. Unlike Oumuamua, Borisov behaved more like a typical comet. It had a coma and a tail, releasing gas and dust as it approached the sun. But its speed and orbit revealed that it too came from interstellar space. Borisov provided the first clear look at the chemistry of a comet from another star. Observations showed that it contained many of the same compounds found in solar system comets, suggesting that the processes that form comets may be similar throughout the galaxy. Borisov was like a small sample of another planetary system, arriving uninvited but carrying valuable information. These discoveries confirmed something astronomers had long suspected. The Oort cloud of our solar system is filled with comets, many of which may one day be ejected entirely, sent drifting into interstellar space. Other stars likely have similar clouds, filled with icy remnants of their own formation. Some of those objects will be ejected too. The galaxy, then, must be filled with countless wanderers, drifting between stars, occasionally passing through other systems. The visitors we have detected are just the first of many we may eventually find. They come from all directions, including from beneath the plane of our solar system. The arrival of such objects highlights the dynamic nature of the galaxy. Stars orbit the centre of the Milky Way, carrying with them their planets, asteroids, and comets. Over billions of years, gravitational encounters with other stars, giant planets, or passing clouds of gas can eject small bodies from their systems. Once freed, these bodies drift independently, following their own paths around the galaxy. Some eventually cross paths with other stars. When they do, they briefly become interstellar visitors, cutting across the host system before continuing their endless journeys. The fact that the first two discovered interstellar objects came so recently is partly due to technology. Our ability to survey the sky has improved dramatically in the last decade. Telescopes that can scan wide regions quickly and detect faint moving objects have made it possible to catch these fast, fleeting visitors. Future surveys, such as those planned with the Vera C. Rubin Observatory, will likely reveal many more. Some of them may arrive from beneath the plane, unnoticed until they are already close. Each one will add to our understanding of the diversity of planetary systems in the galaxy. Studying these visitors is important because they carry material from environments we cannot otherwise reach. Our spacecraft are limited to our own system, and even comets from the Oort cloud are part of the solar system's history. But interstellar visitors bring samples of other systems, pieces of distant worlds that formed under different conditions. By analysing their composition, structure and behaviour, we can test whether the processes we see here are universal. Borisov's chemistry suggested that comet formation is common and similar elsewhere. Oumuamua's unusual properties suggested that diversity is greater than we imagined. Each visitor expands our perspective. The arrival of interstellar objects also blurs the boundary between comets, waiting in the deep below, and those drifting through the galaxy. Some of the bodies in our Oort cloud may eventually be ejected, becoming visitors elsewhere. In turn, some of the objects that pass through our solar system may once have belonged to the Oort clouds of other stars. The galaxy is not divided into isolated systems, but is threaded with these exchanges, a constant sharing of material. Above and below the galactic plane, objects drift, moving from one star to another, carrying with them the history of their birthplaces. The idea that Earth might one day capture such an object is also possible. If the conditions are right, an interstellar body passing near the Sun or a planet could lose enough speed to become bound to our system. Over billions of years, this may have happened many times. Some of the comets we consider part of the Oort cloud may in fact be immigrants, captured from other stars. Beneath the plane, among the trillions of icy bodies, there may be fragments of alien systems, indistinguishable from our own except in origin. The solar system may be less self-contained than it appears. The motions of interstellar visitors remind us of the scale of the galaxy. Even moving at tens of kilometers per second, it takes hundreds of thousands of years for such objects to cross from one region of space to another. Their journeys are vast, their timescales immense. When we catch a glimpse of one passing through, we are seeing just a moment in a voyage that began millions of years ago and will continue long after it leaves us. Beneath the plane, above it, all around, countless such travellers must be moving, unseen but real. Some scientists have speculated about what else interstellar visitors could carry. Beyond ice and rock, they might hold organic molecules, the building blocks of life. If comets can deliver such molecules to planets, as they may have on Earth, then interstellar comets could carry them between systems. Over billions of years, this could provide a mechanism for seeding life across the galaxy, a concept known as panspermia. Whether this has ever happened is unknown, but the possibility adds another layer of meaning to the visitors. They may not only be samples of distant worlds, but also carriers of the ingredients for life. The discovery of more interstellar objects will give us the chance to test these ideas. Missions are already being proposed to intercept such bodies, sending spacecraft to study them up close. Because their arrivals cannot be predicted far in advance, such missions would need to be flexible, ready to launch quickly when a new visitor is found. The challenge is great, but the reward would be enormous. A direct look at material from another star system. Beneath the plane, from above it, wherever they come from, these visitors are opportunities to expand our knowledge in ways no other exploration can match. For now, though, most of the interstellar wanderers remain invisible, too faint and too distant to detect. Only when they pass close do we notice them, brief sparks in the survey data, moving too fast to belong. But even if we do not see them, they are there, drifting through the galaxy. From beneath the plane, from above it, they pass silently, each one a story waiting to be told. The solar system is part of this larger stream, not apart from it. We live in a galaxy filled with wanderers, and from time to time, they remind us of their presence. When we imagine the space above and below the solar system, it is natural to think of structures. The heliosphere, the interstellar medium, the Oort cloud, the halo of the Milky Way. But in between those structures lies something quieter. Vast lanes of space exist where there is almost nothing at all. Not the bustling flow of cosmic rays, not the bright flare of star-forming clouds, but emptiness, thin and silent. Beneath the plane of our system, below the orbits of the planets, through the depths beyond the comets, lie these quiet lanes. They are not voids in the absolute sense, for even here atoms and dust drift. but they are sparse enough to feel like silence on a cosmic scale. The idea of emptiness in space can be difficult to picture. Even in the interstellar medium, which we often call empty, there are still atoms spread across each cubic centimetre. In the Oort cloud there are trillions of icy bodies, even if they are spread across an immense volume. But the quiet lanes beneath us are regions where such objects are far less concentrated. The densities are so low that the chance of a random collision or encounter is negligible. For all practical purposes, these are deserts in space, the wide stretches that separate oases of matter. When we speak of space being mostly empty, these lanes are what we mean. The galaxy is not uniformly filled with stars and gas. It is patchy, structured, with dense clouds here and wide gaps there. Our solar system drifts through these regions as it orbits the galaxy, sometimes passing through a cloud, sometimes through a bubble carved by ancient supernovae, sometimes through quieter spaces. At this moment, the solar system is thought to be within the local interstellar cloud, but beyond it lies the broader local bubble, a cavity of low-density gas. Beneath us, these quiet lanes stretch into that cavity, offering an open view through relatively empty space. The silence of these lanes is not absolute. Cosmic rays still pass through, high-energy particles that cross light years without pause. Magnetic fields still thread through, weak but present, shaping the motion of charged particles. A few atoms of hydrogen and helium still drift, sparse but not absent. Yet compared to the dense clouds where stars are born, these lanes are barren. They are not places where gravity gathers matter. They are not places where new stars are likely to ignite. Instead, they are the resting spaces of the galaxy, the calm between bursts of activity. One way to imagine them is to think of the galaxy as an ocean. In some places, currents converge, waves rise, storms churn. In others, the waters are calm, flat, undisturbed. The quiet lanes beneath the solar system are like those calm stretches. They are not featureless, but they are still. They are where the galaxy's activity slows, where there is little to disrupt the silence. For spacecraft moving outward, these are the spaces they must cross once they leave the influence of the Sun. Beyond the heliosphere, into the interstellar medium, some directions lead through clouds and turbulence, others lead through quiet lanes. Beneath us, the view is tilted toward the latter. The emptiness of these lanes has practical importance. When astronomers look through them, they can see farther into the universe. Dust and gas scatter and absorb light, dimming our view of distant galaxies. But in the empty lanes, the interference is minimal. This is why surveys of the cosmic microwave background or distant galaxy clusters often focus on directions like the galactic poles, which correspond to these quieter spaces. Beneath the disk, the quiet lanes of Sculptor and its surroundings provide some of the clearest windows into the cosmos beyond. It is also in these quiet lanes that interstellar visitors may drift unnoticed. An object like Oumuamua or Borisov could travel for millions of years through such regions without interacting with anything. The probability of encountering another star or planet is tiny. The silence of these lanes makes them ideal pathways for wanderers. A comet ejected from one system could cross through these regions, passing beneath our feet on its way elsewhere, never touching another world. For such an object, the quiet lanes are the highways of the galaxy, open and empty, free of obstacles. The scale of these empty regions is enormous. Distances between stars in our neighbourhood average a few light years. In those spans, there may be little more than thin gas. A cubic metre of air on Earth contains about 25 quintillion molecules. A cubic metre of interstellar space may contain just a handful of atoms. The difference is so extreme that it's hard to picture. Yet this is the reality of the quiet lanes. Space so empty that it is almost nothing at all, stretching for distances that dwarf the size of the solar system. And yet, even in this emptiness, subtle structures exist. Magnetic fields ripple through, carried by currents in the galaxy. Shock waves from ancient supernova still echo, though faintly. A few particles collide, generating faint radiation. Over millions of years, stars drift through these spaces, leaving traces of influence. The quiet lanes are not truly empty, but are the low points in the galaxy's rhythm, the places where activity fades but never fully disappears. Beneath the plane, they extend in long arcs, waiting for the next burst of motion to pass through. For Earth, these quiet lanes matter because they influence the solar system's environment. As the Sun moves through the galaxy, its heliosphere is compressed or expanded depending on the density of the surrounding medium. In a quiet lane, with little external pressure, the heliosphere can expand farther, giving us a larger shield. In a denser cloud, it would shrink, exposing Earth to more cosmic rays. Our planet's environment, then, is partly shaped by whether we are passing through busy regions or through quiet lanes. At present, the local bubble gives us one of these quieter stretches, and beneath our feet, the path leads into more of the same. The idea of emptiness can feel unsettling, but it also brings perspective. The galaxy is not crowded everywhere. It is mostly made of space like this: quiet, sparse, thin. The bright stars and nebulae we see in photographs are the exceptions, not the rule. Most of the Milky Way is made of these quieter stretches, vast deserts between the oases. Beneath the solar system, these lanes extend for light years, silent reminders of how much nothingness lies between the somethings. It is in these stretches that time feels different. With so little to mark the passage of events, with no collisions, no star formation, no bright bursts, the lanes are places of waiting. Comets may pass through, interstellar objects may drift, but the overall stillness remains. For billions of years, such regions have existed, and for billions more they will continue, empty yet essential, connecting the active parts of the galaxy with silence. And so, when we think about what lies beneath us, it is not only structures like the Oort cloud or visitors from other stars, it is also the absence of those things. It is the quiet lanes, the empty stretches that make the galaxy what it is. They are the backdrop, the canvas on which the brighter structures are painted. They may not dazzle, but they define the scale of space itself. Beneath our feet, the galaxy opens into these lanes, and through them, the solar system drifts on its endless path around the centre of the Milky Way. When we think of the Milky Way as a disk, it is tempting to imagine it as perfectly flat, like a great celestial record turning slowly in space. From our vantage point within it, the band of the Milky Way does appear as a thin, even streak across the sky. But if we could step outside and look from afar, we would notice that the disk is not flat at all. It is bent, warped upward on one side, and downward on the other, as though the galaxy were a vast ocean frozen in the midst of a slow wave. This bending is what astronomers call the galactic warp, and it is one of the defining features of the Milky Way structure. The warp was first noticed when astronomers mapped the distribution of neutral hydrogen gas in the galaxy. Radio observations showed that the outer parts of the disk do not lie in the same plane as the inner parts. Instead, the gas is tilted, rising on one side and falling on the other. Later surveys of stars confirmed that the stellar disk itself is also warped, though less dramatically than the gas. The overall picture is that of a disk bent into a shallow S shape, curving above and below the central plane. Above us, the warp lifts part of the disk higher. Beneath us, it dips lower. The causes of this warp are still being studied, but several explanations are likely working together. One possibility is the gravitational influence of nearby satellite galaxies, such as the large and small Magellanic Clouds. These companions orbit the Milky Way and tug on its disk, creating ripples that can warp the structure. Another factor may be the distribution of dark matter in the halo. If the halo is not perfectly spherical, its uneven gravity could twist the disk into a bent shape. Interactions with past mergers, streams of stars, and even the motions of gas in the outer regions all contribute. The result is a galaxy that is not rigid but flexible, bending and shifting like a sheet on water. The warp is not unique to the Milky Way. Other spiral galaxies also show warped disks when seen edge-on. Photographs of galaxies such as NGC 4013 or ESO 510 G13 reveal bent shapes, their outer regions curving gracefully above and below the central plane. This suggests that warps are common features of spiral galaxies, perhaps an inevitable result of interactions with their environments. The Milky Way, then, is not unusual in this respect. Its bent shape is part of a larger pattern, one that shows how galaxies are shaped by both internal and external forces. From within the galaxy, the warp is not immediately obvious. The stars around us are close enough that the bending is difficult to detect with the naked eye. It is only when astronomers map large numbers of stars and gas clouds that the pattern emerges. But even if we cannot see it directly, the warp affects our position. As the solar system orbits the galaxy, it rides along this bent surface, sometimes slightly above, sometimes slightly below, depending on where the warp carries the disk. Our path is not through a flat plane, but through one gently curved by the galaxy's larger structure. The scale of the warp is enormous. The Milky Way's disk is about 100,000 light-years across, and the warp raises and lowers the outer edges by several thousand light-years. Imagine a vast ocean frozen mid-wave, with crests and troughs spanning tens of thousands of light-years. That is the scale of the galactic warp. Above us, the disk arches upward into its crest. Beneath us, it curves downward into its trough. We live within this bent stellar ocean, carried along by its tides. The warp also has implications for the motion of stars and gas. The bending creates regions where material flows differently, where gravity pulls in directions slightly off from the central plane. This can influence star formation, creating asymmetries in the distribution of stars. It can also affect how gas settles, shaping the spiral arms. In this way, the warp is not just a geometric curiosity, but an active part of the galaxy's dynamics. Above and below, the bending shapes the environment in subtle but significant ways. Thinking about the warp also reminds us of how dynamic galaxies are. We often think of them as stable, fixed structures, but in reality they are constantly shifting. Gravity, rotation, collisions and interactions are always at work. The warp is one visible sign of this ongoing motion. It shows us that the galaxy is not a rigid wheel, but a living, changing system. Over billions of years, the warp may grow, shrink or shift, depending on how the Milky Way interacts with its companions and its dark matter halo. The bent shape we see today is only a snapshot of its long evolution. The solar system itself is not aligned perfectly with the galactic plane. The ecliptic plane, defined by Earth's orbit, is tilted by about 60 degrees relative to the galaxy's disk. This means that as we think about above and below in solar system terms, we're already tilted relative to the galaxies above and below. Add the warp to this picture, and the geometry becomes even more complex. Our local definition of up and down is only loosely connected to the galaxy's bending shape. Above us and beneath us, the directions depend on which frame of reference we choose, the ecliptic, the galactic disk, or the warped outer edges. The galactic warp also connects to the idea of waves moving through the disk. Some studies suggest that the warp is not static but oscillating, like a ripple passing through the galaxy. This could be driven by interactions with satellite galaxies, or by the uneven pull of dark matter. If so, then the warp is not a fixed bend but a moving wave, slowly shifting over millions of years. From our perspective, the change would be imperceptible, but over the lifetime of the galaxy, the warp could rise and fall, a cosmic tide shaping the stellar ocean. The image of a warped galaxy also invites us to think of our place differently. We are not sitting on a flat platform of stars, but on one that curves. Above us, the warp lifts the disk higher, carrying stars into an arc. Beneath us, it lowers them into a dip. If we could see the galaxy from the outside, we would notice this bend, and it would be as much a part of our home as the spiral arms or the halo. It is one of the ways the galaxy reveals its history, written in the curvature of its disk. For astronomers, Mapping the warp requires careful observation. Radio telescopes trace the hydrogen gas, while surveys of stars add detail. Infrared observations penetrate the dust, showing the distribution of stars more clearly. Each method contributes to a picture of the warp, confirming its presence and refining its shape. These maps reveal not only the bend but also the asymmetry. The warp is not perfectly even on both sides. One side rises higher, the other dips lower. This imbalance tells us that the forces shaping the warp are complex, not simple or uniform. Beneath us, the dip is different from the rise above, reflecting the uneven environment of the Milky Way. Looking at other galaxies helps us understand our own. When we see edge-on spirals with warps, we are looking at snapshots of what may be happening to us. Some of these galaxies show extreme bends, others more subtle. By comparing them, astronomers can test theories of how warps form and evolve. The Milky Way becomes one case in a larger pattern, part of the study of how galaxies live and change. Our warped disk is not unique, but part of the diversity of galactic shapes across the universe. And so, when we think about what lies above and below our solar system, we should include this bending. The galaxy itself is warped, curving upward and downward in a vast wave. We ride within this bent stellar ocean, carried along by its tides, part of a structure that is dynamic, flexible, and alive. Above us, the crest rises. Beneath us, the trough dips. Around us, the warp shapes the path of stars and gas. It is one more reminder that the universe is not fixed but always in motion, always shaped by the forces that connect everything together. When we picture the Milky Way, the first images that come to mind are usually the bright disk, the spiral arms, and the dark dust lanes that weave through them. These are the most visible features, the ones that stand out in photographs and through telescopes. But surrounding and interlaced with these grand shapes are subtler ones, hidden structures that are harder to see, revealed only through careful observation. These structures include streams of stars torn from ancient galaxies, filaments of matter connecting clusters together, and clouds of gas floating high above the disk. They are the finer threads of the galactic tapestry, the details that tell the story of how the Milky Way has grown and continues to evolve. The streams are among the most fascinating of these hidden structures. Over billions of years, the Milky Way has consumed smaller galaxies, pulling them apart with its gravity and scattering their stars across its halo. These stars do not vanish into randomness right away. For a long time, they remain in coherent trails, moving together along the orbit of the original galaxy. These trails are what we see as stellar streams, long, faint rivers of stars stretching across the sky. One of the most famous is the Sagittarius stream, the remnant of a dwarf galaxy currently being absorbed by the Milky Way. This stream arcs across the halo, wrapping around the galaxy in great loops. From within, we can see its stars as a faint overdensity, a pattern that only becomes clear when large surveys are analysed. Beneath us, above us, and all around, these streams mark the remnants of past encounters. Other streams have been found too. The GD1 stream, for instance, is thought to be the remains of a star cluster disrupted by the galaxy's gravity. The Orphan stream, as its name suggests, no longer has a clear parent, but its stars trace a path through the halo. Each stream is like a fossilised record of a past merger, preserving the motion of stars long after their original system was torn apart. By studying them, astronomers can reconstruct the history of the Milky Way's growth, identifying when smaller galaxies were absorbed and how their material was distributed. Above and below, hidden streams like these stretch invisibly across the sky, connecting us to events that happened billions of years ago. The halo is also threaded with filaments of matter, though these are harder still to see. On the larger scales, the universe is arranged in a cosmic web, with galaxies and clusters linked by long filaments of dark matter and gas. Within the Milky Way, smaller filaments exist as well, narrow structures of stars and gas that extend through the disk and halo. Some of these filaments are magnetic in nature, visible in radio wavelengths as long, thin strands of emission. Others are streams of cold gas flowing inward, feeding the galaxy with fresh material. The exact nature of these filaments is still being explored, but they seem to play a role in channeling matter into the disk, sustaining star formation over long time scales. Above us and beneath us, these filaments are like the invisible veins of the galaxy, carrying material and energy through its body. Clouds are another part of the hidden structure. These are not the dense star-forming clouds of the disk, but more diffuse concentrations of gas high above it. Some are high-velocity clouds, moving at speeds different from the rotation of the galaxy. Their origins are varied. Some may be gas-stripped from dwarf galaxies that pass nearby. Others may be material falling into the Milky Way from intergalactic space. Still others may be fountains of gas thrown upward from the disk by supernovae, cooling and raining back down over time. These clouds are important because they represent an exchange between the galaxy and its surroundings. They are the means by which the Milky Way gains new fuel for star formation and recycles the material blown out by stellar explosions. Beneath us, several such clouds can be seen, drifting slowly as they make their way back toward the disk. The Magellanic Stream is one of the most dramatic examples. It is a long ribbon of gas stretching across the southern sky, trailing behind the large and small Magellanic Clouds, two dwarf galaxies orbiting the Milky Way. This stream was pulled out by tidal forces as the dwarfs interacted with our galaxy, leaving behind a filament of hydrogen that spans more than half the sky. Though invisible to the naked eye, it is mapped clearly in radio observations. To look beneath the disk, toward the southern sky, is to look into the direction where this enormous stream stretches, a reminder that even galaxies themselves can be reshaped into filaments. These hidden structures are not always easy to detect. Streams of stars blend into the background unless large surveys are used to map their motions. Filaments of gas and magnetic fields are visible only in specific wavelengths, such as radio or ultraviolet. Clouds are diffuse and faint, requiring careful analysis to separate them from the background. This is why they remained hidden for so long, only gradually revealed as technology improved. What appears empty or featureless at first glance is, on closer inspection, filled with subtle details. Above us and below us, these structures weave through space, largely invisible but deeply significant. The presence of streams, filaments and clouds tells us that the galaxy is not static. It is constantly changing, absorbing smaller systems, exchanging material with its environment, and sustaining itself through inflows and outflows. The hidden structures are the evidence of this process. The marks are left behind by the galaxy's ongoing evolution. They show us that the Milky Way is not a finished product but a living system, shaped by past events and future ones still to come. Thinking about these hidden structures also connects us to the larger universe. Every galaxy has them. The cosmic web itself is made of filaments on the grandest scale, with galaxies as the nodes where they intersect. The Milky Way's streams and filaments are smaller echoes of that pattern. What we see locally is a reflection of what exists across the cosmos. Above and below, the hidden structures are part of the same web that links everything together, from the smallest cluster of stars to the largest supercluster of galaxies. And so, when we think of what lies above and below our solar system, it is not only the bright and obvious features that matter, it is also the hidden ones, the faint streams of disrupted galaxies, the thin filaments of gas and magnetic fields, the drifting clouds that exchange material between the disk and the halo. They may not shine as brightly, but they are every bit as important, telling the story of how the galaxy grows, survives, and connects to the larger universe. Above and beneath us, these hidden structures stretch silently, part of the intricate fabric that surrounds us. When we speak of above and below, we're using words that come from everyday experience. On Earth, above means sky, and below means ground. Gravity pulls us toward the centre of the planet, and that pull defines direction, in a way that feels absolute. No matter where you are, dropping something will make it fall downward, and raising your hand will lift it upward. These directions are so familiar that it can feel strange to imagine them in space. Yet when we talk about what lies above and below our solar system, we're applying the same words to a context where gravity is not pointing in a single direction, and where there is no surface to define our sense of orientation. In the galaxy, above and below are relative. Astronomers use the plane of the Milky Way's disk as the reference. The North Galactic Pole is defined as the direction perpendicular to the disk on one side, while the South Galactic Pole points in the opposite direction. In this framework, above means looking toward the North Galactic Pole, and below means looking toward the south. But this is a choice of convenience, not an absolute truth. From another perspective, such as the plane of the solar system's ecliptic, the definitions would be different. Above and below are only meaningful when tied to a chosen frame. This relativity of direction can be seen even within our solar system. The planets orbit in nearly the same plane, but each has a small tilt. To say that one planet is above the plane means only that it's north of the ecliptic at a given moment. From another viewpoint, it might be below. Comets, with their highly inclined orbits, cross the plane from one side to the other, so that above and below switch repeatedly during their journeys. The words remain useful for orientation, but they do not carry the same sense of permanence they have on Earth. If we imagine travelling far away and looking back at the solar system, our sense of up and down would depend on our viewpoint. If we looked from the North Ecliptic Pole, the planets would appear to orbit counterclockwise around the Sun. If we look from the south, they would orbit clockwise. Neither is more correct than the other. Both are equally true. Above and below in this context are like choosing to view a map with north at the top or south at the top. The choice changes the orientation, but not the reality of the positions. This relativity extends even further when we consider the galaxy itself. The Milky Way is tilted relative to the ecliptic, so the directions we call above and below in the solar system do not match exactly with those defined for the galaxy. On top of that, the galaxy is warped, bending upward and downward at its edges. Depending on where we choose to draw the reference plane, above and below can shift again. The reality is that in space there is no universal up or down. There are only relative directions, defined by the frames we use to make sense of motion. Despite this relativity, our minds naturally reach for the concepts of up and down because they help us orient ourselves. They provide a way to imagine where things are, even if the choice is arbitrary. Astronomers rely on them as well, because without some framework it would be impossible to describe positions in a consistent way. The galactic coordinate system, with its north and south poles, is one such framework. The ecliptic coordinate system tied to Earth's orbit is another. Both serve the same purpose. They give us a map. Above and below in these contexts become directions on that map rather than universal truths. Thinking about this perspective can shift the way we see our place in the cosmos. On Earth, we are anchored by gravity, and our directions feel fixed. In space, we are free-floating, and our directions are chosen. The solar system drifts around the galaxy. The galaxy moves within the local group. The local group flows as part of a larger cosmic web. At each scale, up and down are redefined. What is above at one level may not be above at another. In a sense, we're always between frames, always oriented by choices rather than absolutes. This does not make above and below meaningless. Instead, it makes them flexible. They are tools we adapt to the scale we're considering. When we ask what lies above the solar system, we mean relative to the plane of the galaxy. When we ask what lies below, we mean the opposite side of that plane. These definitions allow us to describe the halo, the Oort cloud, the interstellar medium, and all the structures we have discussed. They let us map our position within the larger whole, even if the words themselves do not carry the same solidity they do on Earth. On a human scale, this relativity is hard to feel. Standing on the ground, we sense down as absolute. But astronauts in orbit experience something different. In microgravity, there is no natural up or down. Inside a spacecraft, One astronaut's ceiling can be another's floor, depending on orientation. Directions become relative to the vessel, rather than the planet. Extend this to interplanetary space, and the relativity grows stronger. Extend it further to interstellar space, and only chosen frames of reference remain. Above and below are no longer about physical pull, but about perspective. This perspective can be freeing. It reminds us that the universe is not bound to our local sense of orientation. It also helps us see how connected everything is. There is no absolute centre, no absolute up, no absolute down. There are only relationships between stars and galaxies, between disks and halos, between maps and observers. In that sense, to ask what lies above or below is to ask how we choose to look. It is a question of framework, of perspective, of the maps we draw in order to understand. Even the cosmic web on the larger scales reflects this relativity. The universe is filled with filaments and clusters, arranged in patterns that have no single orientation. From one point of view, a filament might appear above another. From a different point of view, it might appear below. The pattern itself has no preferred direction. It is only when we map it that we impose above and below. In this way, the relativity of orientation is not just local to the solar system or the galaxy. It is built into the very structure of the universe. And yet, despite all this relativity, the words remain useful, even comforting. They give us a way to talk about direction, to imagine our place, to ask questions like the one we have been exploring. What lies above us? What lies below? These questions guide our journey, not because up and down are absolute, but because they help us frame the unknown. They are the language we use to turn vastness into something we can navigate. So when we speak of cosmic perspective, what we are really doing is acknowledging both sides of the truth. On one side, there is no absolute up or down. On the other, we can still define them, use them, and learn from them. Above and below in the cosmos are chosen perspectives, frameworks we agree upon. They are not built into space itself, but they are built into the way we explore it. Through them, we orient ourselves within the infinite, and through them, we discover what surrounds us. We have wandered far in thought, lifting our gaze above the solar system and peering into the quiet depths below it. We have traced the boundaries of the heliosphere, felt the subtle protection of its cocoon, and followed the invisible roads of cosmic rays and stellar winds. We have looked through the windows of the galactic poles into clearer skies that reveal the distant universe. We have stood at the edge of the halo, sensing the silent presence of dark matter and the ancient glow of globular clusters. We have imagined the Oort cloud, its icy shell surrounding us in a vast sphere, and the comets resting there in silence until gravity gives them motion. We have noticed the interstellar visitors that pass briefly through our neighbourhood, reminders that the galaxy is shared and interconnected. We have wandered through empty lanes of space, calm stretches that define the rhythm of the Milky Way. We have looked at the galaxy's bent disk, its warp like a tide frozen in a great stellar ocean, and we have followed hidden streams and filaments that mark the remnants of long-gone galaxies. Finally, we have paused to ask what it even means to speak of up and down in a universe where orientation is always a matter of perspective. And now, having followed these paths outward and downward, upward and beyond, it is natural to pause and think about what it means to come back home. To return in thought to the small world where we live, balanced between all of these scales. Home, in this context, is Earth, a planet that feels solid beneath our feet but is itself drifting within these vast layers of structure. Earth orbits the Sun, following its path in the ecliptic plane, a circle repeated every year. The Sun carries Earth and the other planets around the centre of the Milky Way, a journey that takes about 230 million years. The galaxy itself moves within the local group, pulled toward Andromeda, and together the local group drifts as part of the Virgo supercluster. and beyond that as part of the even larger Laniakea supercluster. At every level, motion carries us. Above and below, behind and ahead, there is no stillness. Yet from the surface of Earth, we feel at rest, grounded in the daily rhythm of sunrise and sunset. The contrast between this stillness and the vast motion around us is part of the perspective we carry. We live between the small and the large, between the ground beneath our feet and the endless sky above. When we ask what lies above and below, we're really asking where we fit into this structure. The answer is that we are always between the micro and the macro, between the solid and the infinite, between the known and the unknown. Returning home after such a journey is not a retreat from scale, but an acknowledgement of it. To know that above us lies the galactic halo, streams of stars, cosmic filaments, and the unseen weight of dark matter, is to feel how surrounded we are by mystery. To know that below us lies the Oort cloud, comets in waiting, the quiet lanes of interstellar space, and the faint pull of other stars is to feel how deep the silence extends. And to know that through all of this the Earth spins, carrying us through the seasons and across the galaxy, is to see how connected we are to every part of it. Home is not small when we place it in this context. It is central because it is the place from which we look. From here, we see the above and the below. From here, we measure the distances and map the structures. From here, we wonder about what cannot be seen. Earth is not at the centre of the universe, but it is at the centre of our perspective, and that makes it our anchor. To return home is to return to the point of view that lets us ask the questions in the first place. There is also a human layer to this reflection. The idea of above and below resonates with us because of how we live on this planet. We walk on ground, we look at sky, and our bodies feel the pull of gravity every moment. When we project these ideas into space, we are extending our lived experience into the cosmos. We take words from Earth and apply them to the galaxy, not because the universe requires it, but because it helps us understand. Returning home means recognizing this origin, remembering that our metaphors begin with the simple act of looking up from the ground. As we think about what lies above and below, we also think about how fragile and rare Earth is. The cosmic rays that flow through the galaxy could strip an atmosphere bare if not for magnetic fields and shielding. The comets that fall inward carry both the promise of water and the threat of impacts. The quiet lanes of empty space remind us how unusual it is to have a world rich with air, oceans and life. The warp of the galaxy reminds us that even stars and planets are carried along in motions far larger than themselves. Returning home means recognizing that our world is not separate from these forces but part of them, shaped by them and dependent on them. And yet, home is also where we create meaning. The galaxy may be vast, but it is from Earth that we see it. It is here that we build telescopes, write maps, and tell stories. It is here that we name the galactic poles, define the ecliptic, and trace the hidden streams. Above and below gain their meaning because we stand here, on the surface of a small planet, and ask the questions. Without that act of asking, the directions would be empty. With it, they become guides for curiosity, pathways that lead us outward and back again. To return home after travelling these scales is to hold both truths at once, the immensity of the cosmos and the intimacy of a single world. It is to see that the Oort cloud is real, and so is the patch of sky outside your window. It is to know that galaxies collide, and so do clouds drift across a local sunset. It is to hold in mind that dark matter bends the motion of stars, and gravity bends your step as you walk across the ground. Returning home means weaving the far and the near together, recognizing that they are not separate but part of one continuous whole. And so we return, not to an end but to a pause. We return to the place between, where above and below meet in our perspective. We return to Earth, not as a small speck lost in the vastness, but as the vantage point from which the vastness is revealed. Above us, the galaxy arcs into mystery. Below us, the comets wait in silence. Around us, emptiness stretches, and within us, curiosity stirs. Home is the balance between these directions, the point in space where we notice them at all. And now we have reached a soft resting place in our journey. We have wandered through the spaces above and below our solar system, followed hidden paths, paused at distant shells of ice, and lifted our eyes through windows that look far beyond the Milky Way. And after all of that, we find ourselves back here, in the quiet where you are listening. If you have stayed with me through this long path, I hope it has given you something gentle to think about, or maybe something calming enough to carry you into rest. You are part of this universe, part of all those layers we explored, from the smallest pieces of dust in the Oort cloud to the great bends of the galactic warp. Thank you for sharing this time and this space with me. If you find this kind of journey soothing, you can always return any time and let the science carry you softly onward. And if you wish, you can support the channel by liking, subscribing, or simply letting this play again when you want the stars nearby. For now, let your thoughts drift as far as you like, or as close as you need. Above you and beneath you, the universe is always there, waiting, holding you in its vastness. And here, you're safe, right at home between it all. Good night.